right, welcome back. Let me begin the lecture just by reminding you briefly where I stopped last time. I was looking at an application of effective field theory to a case of flavor physics. Today's flavor is B. And the idea was to look at this type of processes where you, in a machine, an E plus E minus machine, where you can generate B quarks, but yet not have enough energy to generate a top quark. And in particular, I was going to look at the case where you generate an odd number of B quarks. And that is because such a process is suppressed by very small CKM mixing angles. And so it might provide a window of opportunity where the new physics effects might shine through. These are very peculiar flavor-changing new physics effects, but I think it serves as an illustration of using an accidental, or apparently accidental as far as we know, suppression of standard model effects to identify a reaction where new physics might be easier to find. And so it came down to calculating this cross-section. This is a theoretician versions of a not naive cross-section in that it includes the possibility of misidentifying jets of other quarks for B quark jets and for missing some B quark jets. And it involves a certain amount, three experimentally derivable quantities, the efficiencies and the probabilities of mistaking C quarks and light quarks for B quark. And where I last ended with presenting to you my condition for success in identifying a new physics effect in this equation that's summarized by this equation, in which the measured or number of events with KB jets and J total jets with K odd is larger than the standard model by 3 sigma that I call delta. I didn't use sigma here because sigma is used for the cross-section, and I didn't want to repeat the letter. And so the error, 3 sigma, the error is composed of a statistical, systematic, and theoretical error. The theoretical error is generated by QCD effects I did not include, but one could, and thereby this would be reduced, but I didn't do that. A systematic error that depends on the experiment, and it's again something the experiment can provide, and a statistical error that is the usual square root of n effect from statistics. And I've added them in quadrature, which embodies the assumption that these errors are uncorrelated. All this is open to discussion, but let me just continue along this line with these assumptions. And then I introduced a type of new physics. This is, as I mentioned, not the only new physics you can probe using this reaction, but I chose this one. It will contain flavor changing in the quark sector. In the lepton sector, I did not include such flavor changing because that wouldn't be useful for my machine, which is an E plus E minus machine. E plus and E minus are both in the first generation, and therefore these leptons will be in the first generation. The quarks will be one in the third generation and the other in one of the 2 remaining. This can be generated by, as I say here, a Z prime, and as I discussed last time, also by an appropriate leptoquark, vector leptoquark. And here are the results. These are the choices for the various errors and various probabilities for misidentifying them. This thing comes from the people in LEP. And the systematic error as well, the theoretical error we estimated or guesstimated by looking at possible QCD corrections. And the result here is for LEP, which was this, this first line here, and various identities, you get the 3 sigma limits on lambda in TeV. So with a 200 GeV machine, you can probe new physics up to a scale of about 700 GeV, and so on. For a 1 TeV machine and a significantly enhanced luminosity, you can probe new physics up to about 4 times the center of mass energy, which is a reasonable reach. So the thing to get, the numbers here are not as important as the following thing, that if you have a process where the standard model is naturally suppressed, your collider reach will be significantly enhanced beyond the center of mass energy in probing new physics. This disappears once the standard model effects are very large, because in that case, you need an enormous amount of statistics, which in reality will not be available to you. And this is the same type of results in graphs for a half TeV collider and a 1 TeV collider for different kinds of new physics. And this is the area that can be probed depending on I apologize. This should be epsilon b, not TB. Epsilon b. Epsilon b, not TB. Okay. So this is the example. Okay. Any questions? All right. The next step would be to go through formal developments. But before that, I had this nagging doubt and asked around, and it was confirmed that I was less than clear when I talked about the strongly interacting version of the effective theory in my presentation of the various estimates of the coefficients. And if I would like to ask your patience in my going back to that and presenting to you in a little bit more detail how I derive what I call the naive dimensional analysis estimate of the operator coefficients. I will use the board for that effect. And so yeah, okay. So I remind you, what I wanted to do was the following. I was starting with operators of the form, lambda of B, thank you, lambda of B and F, phi over lambda phi to the B, psi over lambda psi to the F, d over lambda to the D. And I'm going to, and this is symbolic. So what I'm doing effectively is I'm associating a scale of new physics, lambda phi, with the scalars, or boson, with the scalars, right? A different scale in principle with the fermions, a different scale in principle with the derivatives. And I am going to try to put, and I'm allowing for an overall coupling constant in front that depends on the number of boson and fermion fields. And I am going to study the possible effects of this type of operators, under the condition that the theory is strongly coupled. And what I mean by strongly coupled is that every time I do a radiative correction, the effect will be of the same order as the tree-level effect. Okay, so the first thing I want to do is look at the coefficient in front. That's the first one I want to do. I'm going to do half the calculation because the other half is straightforward and just a repetition. What I'm going to do is consider an operator that has 2 more boson fields, 2 more, for a reason you'll see in a minute. So I'm going to consider the operator O prime which has two more B's, B plus 2, and then the same number of fermions, and the same number of derivatives. And what I'm going to do is I am going to consider a Feynman graph. I have many colors, so I'm going to use them all. Okay, so I'm going to consider a Feynman graph that has a number of external legs in blue, and such that my operator O contributes to it. So somehow the operator O is one of the vertices inside this object here. Okay? It could be that these lines could be bosonic or fermionic. It could be that some of these lines correspond to some of the fields there. It doesn't matter. And what I want to do now is consider a related graph that involves my O prime here. Okay? And so this graph will look exactly the same. Exactly the same. So this is a graph. I already screwed up. Okay. Green. All right. It has the same number of external legs, but now my O prime, which contributes to it, my O prime that contributes to it has two additional bosons to play with. And what I'm going to do with those two bosons, I'm going to take them out and join them. I'm going to assume that they can be joined. And so I have an additional pair of bosons that I will join. Oops. So I have the same graph I had before with an additional tadpole. That's the only thing I got. An additional tadpole. This is a radiative correction to this guy. By the strong coupling assumption, the effect of this guy will be of the same order as this guy. Okay? But this I can calculate, I can estimate. And that's why this is called naive. I'm not going to calculate anything. I'm just going to estimate everything. Okay, so what is the difference between this guy and this guy? It will be the following factor. This guy has a factor of lambda BF and stuff in front of it, because I told you this guy is inside. This guy has a factor of lambda B plus 2 and F, has an additional 2 powers of 1 over lambda phi squared from here, and it has a loop. For the loop, I am going to simply replace momenta by lambda. I am tacitly assuming that because this scale lambda is associated with a derivative, it is then associated with momenta. It will serve as a kind of cutoff regulator for all integrals in all subsequent estimates. So what is that? Well, the tadpole gives me 1 over lambda squared for the propagator, lambda to the 4th for the loop integration, and my standard punishing factor of 1 over 16 pi squared because I have a loop. And the result from substituting this instead of this should not change the order of the expression. That is, since this is of the same order as this has to be of the same order as this. And I will stop putting a squiggly line. I'll just put an equal sign. But please remember, these are all estimates. So I have this, that lambda BF is equal to lambda squared over lambda phi squared, I don't want to write this. I want to write it with a 4 pi in front. 4 pi lambda phi all squared lambda b plus 2 f. So I've related the coupling constant with 2 extra boson lines to the one with 2 fewer, to the one to the original one. And I can keep on doing this with more and more things. And so I can solve this for lambda b. And you get the following thing. Lambda b and f is equal to of 2 and f. And now I can do the same thing for the fermions, but I will not bore you with that. I will just tell you the result. The only difference is to remember is that the operator in question, when you add a fermion, well, it has a lambda psi instead of lambda phi. The propagator, however, has 1 over lambda, because the propagator is 1 over p slash minus m. It's not 1 over p squared minus m squared. So there will be, instead of a 1 over lambda squared from the propagator, I should say, no, this is propagator. And this is the loop integral. For the fermions, there will be a 1 over lambda, but there's still a lambda to the, from the propagator, lambda to the 4th on top. So, putting it all together, and here I am going to have to erase. So I'm going to have to erase this thing, because I don't have any more space.
Excuse me? Hello?
No? Not space?
Can I ask a question?
What's that?
Can I ask a question?
You can ask a question.
So here the lambda in the last line is not related to the lambda in the d by lambda, right? This is different.
This lambda?
Yeah.
I thought I'm associating the lambda without subscript to all momenta, as a scale of all momenta, the cutoff scale of momenta. That's why I put it here with the derivative, because it's kind of a momentum.
Okay.
Okay. None of this is rigorous in any way. That's the way I'm thinking. I'm telling you. Okay. Okay. That's what I'm thinking. I'm not. If this is the logic I'm following. It might be flawed, but I'm telling you the logic. Okay. So erase. Okay, going once, going twice, gone. So I can do exactly the same thing with the fermions and get the following expression. This guy then this horrible thing, 4 pi to the 2/3 lambda psi over lambda to the 3/2 f times lambda 2 and 2, which I will call lambda bar. So with this argument, I've managed to get rid of lambda bf as a function. The b and f dependence of this little lambda is now explicit, and I have only one overall coefficient, lambda bar. What I'm going to do now is the following. I'm going to substitute this thing here. I'll get a new expression for O. And next, I'm going to consider a general graph with several of these operators O inside it. And again, use the strong coupling condition as I defined it. So again, I have no space. I'm going to put this here and tell you what I get. Okay? So I'm going to erase my O prime and my graphs, and I'm also going to erase this. I'm going to put it back. But it will reappear in a second. So I'm going to substitute then the expression I had for this lambda BF in here. And I get the following thing. First, you will notice, in fact, that the scales that lambda phi and lambda psi just cancel out, just go away. And they're replaced by particular combinations of lambda. So I get this lambda bar, lambda to the fourth. Oh, in the original expression, I knew I was missing something. In the original expression, I had this. Oh, just a minute ago, without erase, BF. And this is not right. I'm sorry. There's a 3/2 here that I've forgotten. I apologize. And to have the right units, there's a lambda to the fourth here that I forgot completely. So I forgot those two things. I apologize very much. This is the original expression we had. For the O prime, everything looked the same, but I also screwed up by forgetting this guy and this guy. I'm sorry. I copied wrong. But now I'm going to replace this. That doesn't affect the calculation I did before at all. Okay? Because I just looked at the bosons. If I had done it with the fermions, I would have found myself in trouble because I'd forgotten this 3/2. But the result I presented to you is correct. All right, so I'm going to then replace the expression for lambda BF, and the result is the following in red. This now becomes the lambda bar, just a thing that doesn't depend on B and F. There is here, instead of this, lambda, let me write like this, lambda over 4 pi. So instead of lambda sub phi, I have that. And now, and here, I have, instead of lambda psi 3/2, I get lambda, the same lambda, 3/2, also divided by 4 pi. So this is the result of getting rid of the B and D and F dependence of the coefficient in front using the argument of strong coupling. All right. Yes? Excuse me? Where are you? Left on. Okay. Yes? No, actually, it works out with the 4/3, with the 2/3 and everything. It's just the 4 pi. I checked. I mean, I'm happy to go with you with the calculation step by step for the fermions. But this is exactly 4 pi. There's no 4 pi to the anything there. Really, there's no. Okay. Other question? All right, now I want to consider a generic Feynman graph that has, I don't know, looks like, I don't know, has loops, has external lines, you know, for all I know, has external lines, has internal lines, you know, like this. I don't know, it has other internal lines, things like this, okay? A Feynman graph, a generic Feynman graph. And these vertices are all produced by a set of operators like this, O1, O2, O3, OV in general, okay? And I want to estimate this graph again. And I am going to, okay, so this is, I'm going to estimate this graph. What is this graph supposed to do? It's supposed to make a radiative correction to some vertex with one, in this case, with 4 external legs. This vertex, so the external line, this is a, okay, this vertex will also correspond to an operator. So, this is a renormalization or a radiative correction. Perhaps, let me call it like this, a radiative correction to an operator O. To O. And the vertices from a set of other operators O little v from 1 to big V. V is the number of vertices, total number of internal vertices. And I want to do my estimate in the same fashion. So what do I have? I'm going to estimate this graph. I have a factor of lambda bar, lambda to the 4th, to the V, because I have V vertices. Okay? I have a factor of 4 pi over lambda from this guy to the sum of B sub V. I have a factor of 4 pi over lambda to the 3/2 to the sum F sub V. Okay? I have a factor of 1 over lambda to the sum of D sub V. Oops. That comes out of the vertices, just the vertices. And now I'm going to estimate the loop integrations using the same thing, replacing every momentum by lambda. It's going to do. So what do I have? 1 over 16 pi squared to the power of loops. Then I have a lambda to the 4L, because every loop integration is d to the 4 some momentum. Then I have 2 powers of lambda inverse for each boson line. And these are the number of internal boson lines. 1 power of lambda inverse for each of the fermion internal lines. So IF is the total number of internal fermion lines. And now there is one more thing I want to point out. The momenta I'm replacing by lambda, but I cannot do that for every single momentum because the operator I'm looking at has d derivatives. This corresponds to d external momenta. These external momenta have to be taken into account in this calculation. Since I am taking out the external momenta, this must be compensated by dimensional reasons by precisely the inverse powers of lambda. So this is the graph. This whole thing is here, my angry graph. Okay. It looks very messy, and to be honest, it is very messy. But there are a bunch of graphs, there's a bunch of relationships that can really help us in simplifying this. I'm going to give you the relationships, and then I'm going to give you what the simplified expression looks like. Okay? So here are the relationships. First, the sum of B sub V is equal to 2IB plus B. This B is this B because this is the guy that this is supposed to do radiative corrections to. The sum of F sub V is 2IF plus F. And then we have our old friend that L is equal to I, the total number of internal lines, minus the total number of vertices, plus 1. And you will not believe what you get when you put it all together. You get that this coefficient is this whole thing is lambda bar, lambda 4, to the V. No, I'm sorry. What I got? Yeah, sorry. No, this is not. No, sorry. Yeah, because there's a bunch of 4 pi's. You get the following thing. 16 pi squared lambda bar to the V times lambda bar lambda to the 4th. That's a coefficient. Which is a very nice simplification. All this, I agree, it's worth going through the mess if you have nothing better to do to get this result. This is the coefficient of the original guy. This loop correction, what it does, it gives you the original coefficient times this power of 16 pi squared lambda to the V power. Okay? What's that? Yes, I have not put any constraints on anything. It's just it's a completely general hand-wavy argument. Okay? So with the assumptions I've made no other assumptions. So with this thing, you can calculate a new coefficient produced by this guy for this operator.
I have one doubt. Is V with all vertices or just external vertices?
No, V is all vertices. All V's are all the internal vertices. All the internal vertices. All these. In this particular graph, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 guys. Okay. Okay. All right. And now, finally, the condition for strongly coupled is that this guy has to be the same order as this guy, irrespective of anything that, irrespective of the graph. And that can only happen if lambda bar is 1 over 16 pi squared, and we're done. Okay? So lambda bar is 1 over 16 pi squared. And now we're really done. So we have a full estimate of the vertices in terms of a single scale and the condition of a strong couple. The assumptions I've made originally and throughout was that all momenta are associated with the scale lambda. I've replaced that I'm going to use as a cutoff, and I replace every single integration, every single instance of a momentum by lambda, except for the external ones, giving rise to this particular factor here. Doing that, and again using again and again the condition that the theory is strongly coupled, I found an expression for the coefficient of the operator that replaced the original, in principle, independent scales by these, which are related but except to the momentum cutoff scale or the momentum scale by a numerical factor. And then considering this generic form of the operators in a generic graph, and again using the expression for strong coupling, I find a consistency value for lambda bar, 1 over 16 pi squared. And that is what I tried to do too briefly in the couple of slides a couple of lectures ago. Any questions?
So, the question is, like if you are doing a higher order correction, and then if you get these different operators which are of the same order as the varied corrections, then how do you truncate?
You never truncate. No, no, no. The problem, okay, so the question is, how do you truncate? I can't. I can't truncate. The only thing I can do is estimate in this way. And so extract, you don't truncate, you extract certain useful information from these things. You cannot do a full perturbative calculation under control. You can't. I'm just telling you, it's not under control.
This is just
exactly, it's not under control. Exactly. So it's a strongly coupled theory. What you can do sometimes is extract some particular interesting information. Certain radiative corrections actually can be calculated. Say, loop, you have many operators. You can calculate the running of some of the coupling constants, the renormalization group running of some of the coupling constants, using the fact that only operators that you have, I'm trying to jump ahead. If you have a set of leading operators, you can calculate the corrections running of their couplings using the effects of these leading operators only. You don't have to consider subleading operators, the effects of
that would be perturbative.
It looks perturbative, but the theory in itself is not perturbative. The running of the couplings can be calculated perturbatively.
If you have like a higher, like a large anomalous dimensions, then this cannot be done.
No, you can't. You can't. I mean, but I'm sorry, I can't. Maybe you can, but I don't want to make assumptions.
No,
I can't.
This is just based on the fact that this is just naive dimension.
Exactly, exactly. This set of hand-wavy arguments is called naive dimensional analysis because if you go through this carefully, the only thing I'm using is the dimension of the terms in the Lagrangian is 4. That's really what I'm using. That's a big thing. If you by the way, if you live in a different universe, like 11 dimensions, the factors change. Okay, the factors change. Okay, good. I mean, but you can do the same thing. Other questions?
One more question.
Please.
Like typically for loop diagrams, what is the kind of regularization one must use?
Okay, the question was, what kind of regularization does one use in loop diagrams? In actual calculations, you use dimensional regularization because it's just easier. And it has to be done carefully, and as every calculation does. But usually, the practical application is dimensional regularization. Some people use cutoff. Some people use, which is problematic. Other people use polyvillars, which is has its own issues. Depending on what application you want. If you want to just, get an idea of how it's going to go, use a cutoff because it's faster. If you want to get it right, use dimension regularization. Other questions? All right, then we can go back to our regular programming. And I still have 20 minutes. Oh, wow. Okay. So more, oh, now, yeah, I just need the lights off because, thank you. Thank you. So I'm going to go back to this thing, and after one phenomenological application of the theory for the case of weakly coupled, I'm going to go back and talk a little bit about the formalism itself. And I've been telling you that you can dispose of operators that are, in a sense, equivalent. That is, that they are equal when the equations of motion are imposed. I know that was vague. That was on purpose made vague in my comments. I am going to make it very precise in the following slides. Or that's my intent. That's my hope. So I'm going to talk about something called the equivalence theorem. You all probably have heard of the equivalence theorem. This is not this equivalence theorem, the gravitational mass equal to the inertial mass. Not that. There is another equivalence theorem that says that the longitudinal components of the gauge bosons and those of the would-be Goldstone bosons in a spontaneously broken gauge theory are the same. That is not this equivalence theorem. Unfortunately, the equivalence theorem sounds really nice, so everybody wants to use the label. So you just have to deal with it. Remember the equivalence theorem. This is the equivalence theorem, if you wish, for EFG. Okay, so I'm going to talk that. All right. So the equivalence theorem I'm going to talk about is the following. Suppose you have your effective Lagrangian that has a light component and a bunch of other effective operators. And I've neglected to put in this lambda to the n, whatever, just because I didn't want to clutter the notation more than needed. Now imagine that you have two effective operators such that they obey this relationship. This is an explicit relationship. You look at one operator, look at another operator, and see if there is some constant such that if you multiply the first operator by it, subtract the other operator, you get something times the classical equations of motion. Okay, this is by definition the classical equations of motion. This slight is the integration of the light Lagrangian. I am going to imagine that these guys have been ordered in a leading, subleading, sub-subleading, blah, 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 blah. These are the leading guys. If you want to imagine, you want to consider the effects of the subleading guys not listed here, and you find two operators that do this, this expression is slightly modified. I can talk to you separately about it, but let's not complicate matters more than needed at this point. These are the leading operators, leading corrections to the light theory, and I find two operators, O and O prime, that obey this relationship. Then, what the theorem says is that the S matrix, anything that you can observe, let me emphasize this, anything you can observe, not anything, anything that you can see, will depend only on this linear combination, not on anything else. It will not depend on the coefficients of O and O prime separately, but only in this particular linear combination, where this particular quantity A is the number here, this precise number. Okay? That is the equivalence theorem. Why is it interesting or useful? Well, because if every observable, and this is, again, let me try to be very clear. This doesn't mean that these operators are the same. It doesn't mean that these operators come from the same new physics. It doesn't mean any of that. What it only means is that at low energies, their effects always come up in this linear combination. The effects of these operators are summarized by how things depend on their coefficients, and the coefficient dependence is always like this. Therefore, if I set this guy to 0, I lose nothing, because there is no way of differentiating from the effects of this guy and this guy at low energies. In fact, when you measure quantities, and if I tell you this quantity always contains this linear combination, well, it is this linear combination that you will measure, not this guy and this guy separately. So you might as well get rid of this guy and measure and obtain constraints, values for this CO, keeping in mind that in fact CO might represent a linear combination of contributions. The high energy theory, whatever it is, may generate this guy, or may generate this guy, or may generate both. At low energies, you can't tell the difference. If it only generates this, well, then you will measure it. If it only generates this, you will still measure it, like that. And then you can't tell the difference. So the equivalence theorem says that operators like this, that have this relationship, cannot be distinguished at low energies. That is, their effects cannot be distinguished at low energies. If you don't look only at S matrix elements, you look, say, at things you can't measure, propagators or something like that, vacuum polarizations that you can't measure in general, then you will find that C and C prime appear separately. But whenever you look at an observable, that independence of C and C prime is proven illusory. So they always come up like this. And so what one does, if one doesn't like to deal with many coefficients, is to go tediously through the list of operators you can construct and eliminate either O of O prime, whatever strikes your fancy, from the list, knowing that they're redundant as far as low energy observables are concerned. Okay, all right. So this is a result. This is the comment that I was making a little while ago. That what I'm going to do is calculating the situation where, and I forgot to change. This is the Lagrangian. I used the wrong font. I apologize. So this is curly L. This is the Lagrangian. Is valid to lowest order in the effective theories corrections in the Lagrangian. If you have higher order corrections, then you have to, instead of using the light theory, you have to use the light theory plus the effective theory terms up to the one below you're interested in. So instead of having just this here, you have to do this. The calculation is the same. Actually, doing it for general K, it just introduces more complication with any conceptual advantage. And let me again superemphasize, this is a property of the light physics. This property at the low energy limit, right? Because the equation of motions that you're imposing are the light theory's equations of motion. Has nothing, provides no information about the heavy physics. It doesn't mean that somehow the heavy physics has to generate operators always in this type of linear combination or anything of the sort. Okay. It's just a property of the light theory. Now, instead of doing a full-fledged quantum theory calculation to begin with, I'm going to do a quantum mechanical calculation. Yes. So, sorry, just to say, he's younger.
Again?
Yes.
Can you go to the last slide? So in this relation, is there any limit of energy both sides, let's say E equals to something?
the question is there any limit in the energies in which I am doing this calculation? No, this is supposed to be an operator identity. So you have operators, operators, you know what, I might as well do an example. I'm going to erase here and give you an example, because otherwise I'm just talking in empty space. I'm going to do a very simple case because it's useful. Your light theory is just a scalar field. It's a lambda phi to the fourth. Okay, it's 1 d phi squared minus 1/2 m squared phi squared minus 1 over, 4 lambda phi to the fourth. Okay? Okay. The equation of the motion. Minus 1/2, that's not even true. Equation of motion. Okay. Now, let me consider one operator that has dimension 6, just for fun. Okay? Just operator. So, operator dimension 6. It's dimension 6. Okay. Now let me make my life simpler. Okay. 3 and 1. I like this one. That's right. So I'm not going to put 1 here. Okay. And the reason for that is I'm going to write this using this guy. Okay. Bear with me. So I can write this as phi cubed box plus m squared phi plus lambda phi cubed minus things, minus m squared phi 4 minus lambda phi 6. I didn't, okay? I am going to call this O. No, I'm going to call this minus lambda O. Minus lambda O plus lambda O. I'm just going to call it plus lambda O. No, minus, plus. And I'm going to call this guy, in fact, O prime. O. Pardon me? Lambda will become A. I mean, bear with me, okay? Lambda, just wait. Wait. So I've proven the following thing. Oh, proven. I just, it's made the simple calculation says the following thing. That this is phi cubed minus, I'm going to put like this, minus delta okay? So what the theorem says is that I can place, whenever I have this guy, I can replace it by this guy. This lambda plays the role of A. This plays the role of the curly A that I had. And what the theorem says, again, is that if you have a general effective theory, you write all the dimension 6 operators, you come to this guy and say, can get rid of the guy, and I replace it by these two guys. This term is innocuous. It's a renormalization of the phi to the 4 term in the Lagrangian. This is a bona fide dimension 6 operator. Okay? Does that answer the question?
One more thing is that, let's say, maybe it's not a very question, but let's say is
Say
that
again.
So-
Use microphone.
so? If there is some non-linear relation between O and O prime, let's say, then is it infer anything?
No.
Or
If you have AO is O prime minus O prime cubed equal to something like that, is that what you're thinking?
yeah.
No. Well, in reality, what happens? If it's AO minus O prime cubed, I called O prime cubed O double prime, and I now have AO minus. But if you have a relationship of the form AO plus BOO prime plus CO prime or double prime or some other complicated thing involving O and two other operators or something like that, this theory doesn't apply. This is it.
Okay.
There's nothing more beyond this. This is going to be it. Okay?
Yeah.
I'm sorry, your question?
Just a very nice question. Like this is very similar to this this decoupling benefit.
This is different from the question whether this is related to decoupling. This is different from decoupling. I'm not getting rid of operators. This is a I'm assuming decoupling, but I'm not getting rid of operators. The only thing I'm saying is that at low energies, if you have this guy and you have this guy, you cannot tell them apart. The effects of each are the same. And on that happy note, I will finish. This lecture. I will come back and give you the example using quantum mechanics, which is, I hope, familiar to all of you. And I think it provides a simple gateway and rather painless to how the equivalence theorem works. More questions? All right, then I'll see you this afternoon. Thank you.
So we have tea outside, and we will come back for the next lecture on physics. And then today we will have a photography session after that lecture. So please be around with smiling faces. So dimension 5 will always give you left right. Dimension 7 will give left right, and dimension 9 will give so that's an interesting decision. High dimensions are polite. That means yeah, it's very simple. That you can write explicit interaction terms. Hello. Am I audible? Okay. All right. So, welcome back, and in this lecture, as you can see, that I am going to talk about the Higgs physics and how effective field theory or effective standard model effective field operators can contribute to some of these observables related to Higgs physics. That is what I am going to talk about. And once again, there are many possibilities that one can talk on, and however, I will restrict myself to a couple of examples, and we will see how these things are interesting in the present context of the searches that are going on for the Higgs physics. Okay, so it is customary to remind ourselves that we already have talked about many times, but it is once again still helpful to remind ourselves that the standard model gauge group SU3C cross SU2L cross U1Y via spontaneous symmetry breaking by a suitable choice of the Higgs doublet with a hypercharge of y equal to half breaks the gauge group into a remnant SU3C cross U1 electromagnetic, and which generates basically the standard model fermion masses and gives rise to massive weak gauge bosons W plus minus and Z. And you remember, this is the Lagrangian that we talked about, which includes the scalar potential involving this guy in a gauge invariant way. The parent symmetry is still SU3C cross SU2L cross U1Y. Well, by the way, SU3C does not work too much here because it is only transforming under this SU2L cross U1Y. And once you choose this mu square in the scalar potential less than 0 and then identify the minima associated with the scalar potential, it shows infinitely many degenerate minima, and once you choose a specific one that breaks SU2L cross U1Y symmetry, and one specific choice of this vacuum is like this, where you assign the wave to this guy phi 3 by V plus Hx, where this is the fluctuation about the vacuum and which is the Higgs boson, and the other massless fields become the Nambu-Goldstone bosons, and they are sort of responsible for giving masses to this W and Z bosons. And then we also have the Yukawa interactions, which once you put the vacuum expectation value to this phi field here will generate the electron masses. For this term, you generate the down type quark masses. Via this interaction, you generate the up type quark masses, and in the standard model we do not add the right handed neutrinos, but that story we have already talked about. Okay, but the question that we are asking is that how do we know what kind of Higgs that we are actually looking for. So, the subsequent slides that I am going to talk on is essentially devoting that same idea or the same question, that the Higgs that we have discovered is what kind of Higgs it is, and how the presence of effective operators beyond dimension 4 can help in illuminating that thing. So, once again let me sort of remind you that within the standard model Higgs, these are the interactions with the gauge bosons which stems from this kinetic term, and the Higgs interactions with the fermions get generated from the Yukawa interaction, and these vertices are proportional to the fermion masses, these are the proportional to corresponding gauge boson masses. And then there are self interactions and which are from the scalar potential itself, and there is a trilinear Higgs interaction, and this is a very crucial one because this is ideally not there in the scalar potential, but once you write phi equal to V plus H and expand this potential, then you actually generate this
trilinear term. So, this is very important to probe in order to know the symmetry breaking mechanism that actually is there. And so, in a generic sense, you can say that measurement of all these couplings and the parameters associated with the scalar potential will actually be able to confirm the nature of the Higgs. And here the effective field theory comes in and asks us, gives rise to some kind of questions that helps or in a sense affect our observational consequences, and that is what we are going to talk about. And there is a video before we proceed further which I want to just show. So, this is from CERN, and this is actually about the discovery of the Higgs boson, which I just wanted to show you. I mean, not always. It's the CERN buses flying actually, Jose. So, this is the LHC.
Today is also a special day because we hear two presentations from the two experiments, ATLAS and CMS, on their update on a search for a certain particle.
I will give the status of the CMS Higgs search. The standard model is here, is shown here. This is what we know. These are the particles making up the standard model that we've known and seen up till now. But there's one piece that's missing, and that's what we call the Higgs. It's very interesting. It's pretty much in agreement with the standard model at 95% confidence level. Standard model's here, this is what we're measuring. So it's a bit off, but again, we need more data. We've seen this, we calculate this, and we conclude by saying that we have observed a new boson with a mass of 125.3 plus or minus 0.6 GeV at 4.9 standard deviations. Thank you.
ATLAS is very pleased to present here today updated results on standard model Higgs searches based on up to 10.7 inverse femtobarn of data recorded in 2011 and 2012. And it's a big honor and a big emotion for me to represent this fantastic collaboration at this occasion. So, quantification of the excess. This slide shows, again, the usual p-value as a function of mass, and also the significance now as a function of mass. This distribution is extremely clean, except one big spike here, in this region here. So, zooming in this region.
You know the name of this person, right?
Well, I would like to add my congratulations to everybody involved in this tremendous achievement. For me, it's really an incredible thing that it's happened in my lifetime. It's taken...
Yeah, I think we can go ahead now. Okay, let me bring me back my slides. Where is it? Yeah. No. Once again it started. No more. Sorry. Yeah. Okay, all right. So, yeah, that was a fantastic discovery of Higgs, and yeah, it's once again interesting to note what are the Higgs production channels at the LHC, and this is what is called vector boson fusion, quarks exchanging W or Z, producing Higgs with 2 jets, and this channel is what is called the gluon fusion channel, and this is what is called the Higgs-Stralsund process, because you are producing an Higgs in association with a W and Z, and then there is a Higgs with a Z via this gluon fusion. There is a production mechanism with top pair, and this is also an interesting channel where you actually produce Higgs in association with a single top, and that is also very interesting. At the collider, when you look into the results that people have obtained so far, for these different channels that we just talked about, they provide you with some term called mu, and this is this parameterizes basically sigma times the branching ratio of the observation divided by sigma times the branching ratio in the standard model. What it means that if this mu value is observed at 1, that means your observation is very consistent with standard model. If not, then there is a possibility of saying that what we are seeing has maybe something more than what the standard model offers. So, you can see this list, and this is for 13 TeV with 138 femtobarn inverse from one of these detectors called CMS. You showed that there are 2 detectors which were searching for Higgs. One is called the CMS and the other is Atlas. So, both confirm the signal of Higgs, but this was showing that there is some deviation in the ZH channel and WH channel, little bit of discrepancy with vector boson fusion, but otherwise more or less consistent with mu equal to 1. Something similar happens in the Atlas case, and I think this so this is in the y axis you have the different production modes of the Higgs boson, and on the x axis basically these are the Higgs decay branchings that you through which you probe these channels, like Higgs going to BB, WW star, tau tau or ZZ star, etc. So, in this way you can see that mu equal to 1 is this line, and whatever the little deviations that you actually spot there is basically showing that the observations that have been made so far is not absolutely consistent with what standard model provides. So, this gives you an opportunity to probe the possibility of new physics entering into the Higgs searches in some way for those cases which actually deviates from the standard model observation. Then there are also measurements of the Higgs couplings, and usually what the way that people parameterize it is once again via something called a kappa, which is essentially the ratio of G observed by GSM, where G observed is the coupling that you actually could extract, and the GSM is the coupling which is actually predicted from the standard model Higgs isodoublet. And once again you can look into this list and find out the deviations. So, in principle if kappa is equal to 1, that basically means that you are pretty consistent with standard model, and once you deviate from that, that gives you an opportunity of probing the Higgs coupling beyond the standard model. The question is if there is something that contributes to that. So, this is an exercise which people do. Now, let me bring back to the list of operators which Jose introduced yesterday, the dimension 6 ones. Why dimension 6 ones? Because in the dimension 5 we have already seen that only couple that modifies the Higgs neutrino coupling, and that does not affect our observations to a great extent. So, in this dimension 6 operators we have operators involving the yes.
Sir, I have one question.
Yes.
Sir, my question is that is the wave, the 246 GeV, it's experimentally measured?
The wave cannot be measured unfortunately, but
the mass is measured.
The consistency, yes, mass is measured.
But coupling is also not directly measured, that lambda?
The trilinear coupling, yeah, the quartic coupling or whatever you say that.
Yes.
I think that is vaguely measured. The lambda measurement is not that in the kappa framework. I think lambda is not included. Yeah, because it's difficult at LHC to measure the trilinear, because that lambda coupling will be best measured via this triple Higgs interaction, right? So that is difficult to measure at LHC.
Okay, then from where did this 246 experimentally came that it's the wave we are taking?
No, it's just a consistency between the MW and MZ, because there is a relation of mz square equal to mw square cos square theta w.
If our rho equal to 1.
Right, rho equal to 1. So that actually essentially confirmed what is the value of the vacuum expectation value. So we couldn't measure the value of the vacuum expectation value, but the consistency relation between the measurement of Z mass and the W mass and their interrelation confirms what is the vacuum expectation value that the isodoublet should produce. Yeah.
Okay.
So it's not a direct measurement of the vacuum expectation value, if I understand correctly, right? The mass of the W or mass of the Z, because we know also that the weak couplings are known,
yes,
G and G prime, because that gives you the measurement of tan theta W equal to G prime by G, right? And we know sin squared theta W is 0.23. So that determines the G and G prime, and once you know those, you know MW is simply G into
yes.
V
by yes.
GV by 2 or GV or something like that, whatever.
Yes.
Yeah. Yeah, well, this is what the picture actually shows. This kappa framework, which shows, okay, all right, we have measured the Yukawa couplings to a great order of precision, but not yet there to fully confirm that it is coming from the Higgs isodoublet, the one that we postulated. Yeah, exactly. So that's the question that we are asking, that the Higgs that we have discovered, whether it's a pure standard model like Higgs, or there lies any option to go beyond the standard model, including another singlet, give it a vacuum expectation value, put together. All these questions are open, and you can constrain your observations from this kind of measurements. So those windows are not completely closed yet. That's what we can say. Okay, so let's proceed. So let me sort of come to this dimension 6 operators. So you have gauge field operators. You have the Yukawa modifiers, which will come from this kind of terms like psi square phi cube, and it's obvious that it will actually come from this kind of terms. Then you have dipole operators coming with this inclusion of sigma mu nu. You have the Higgs current operators, which has this phi tilde dagger d mu phi with up bar gamma mu dr, and it's same, you can do it with all the other doublets that are there, not only the left handed doublets but also with the right handed singlets. And then you have the bunch of 4 Fermi operators, and these are also classified like all these combinations which Jose discussed, that there are L bar L combinations, R bar R combinations. That means all the fermions that are introduced here to construct these operators are left-handed doublets. Here they are right-handed singlets, and in this case they are a combination of left-handed doublets and right-handed singlets. And then you can also have a tensor kind of operator here with a combination of L bar R bar L. And then there are some operators, the others are called the scalar operators of that kind, and then there are B violating operators also which you can constitute. So now before proceeding further, I would like to just give you a little insight about the CP symmetry and the fields. So we would like to find out the CP transformation of the field strength tensor. So, what was the definition of the field strength tensor, which is actually B mu nu equal to del mu B nu minus del mu B mu. So, this is something that we know. The parity of del 0 remains the same, where parity of del I takes a minus sign. Parity of B naught is once again the same, the parity of B I is minus B I. What about the charge conjugation? Charge conjugation of del mu is plus del mu, where the charge conjugation of B mu is minus B mu. Now, here you would like to ask this question, that why the charge conjugation on B mu gives you a minus B mu. The answer to that is as follows, that when you do this charge conjugation operator on the psi bar gamma mu psi, then it actually picks up a negative sign. And if you want your B mu psi bar gamma mu psi to remain invariant under C, then the B mu has to pick up a sign under the charge conjugation. Now, you can use these results to actually find out the parity transformation on B00, which remains the same, Bij, which remains the same, B0y will pick up a negative sign, and Bi0 will also pick up a negative sign. In general, you can show that the parity acting on B mu nu will give you B mu nu. What about the CP transformations? Having P acting on B mu nu gives you B mu nu, you can say that Cp on B mu nu is essentially C acting on B mu nu, and following this result, you can say that the Cp acting on B mu nu will give you a minus B mu nu. What about the conjugate field strength tensor, which is B tilde mu nu? We know that it involves a Levi-Civita symbol, or antisymmetric tensor of rank 4, epsilon mu nu rho sigma B rho sigma. And this is something that you can verify, that the P on epsilon will actually have a minus sign, minus epsilon, where C on epsilon will remain the same. And if it is the case, then unlike the Cp transformation on B mu nu giving you a negative sign, here you can see that P acting on epsilon mu nu rho sigma will actually take another additional sign, and that will get cancelled when the C acts on this field strength tensor and changes its sign. So, B mu nu tilde remains invariant under Cp transformation. So, therefore, the question is that now you come to this question, that what happens to the Cp transformation on the Higgs doublet. The P of phi remains phi, C of phi gives you phi star. So, Cp acting on phi dagger phi essentially gives you phi dagger phi. Cp transformation of the operators which concerns us. Now, say for example, take this operator O phi b, which is like phi dagger phi B mu nu B mu nu. What will be the Cp transformation? Cp transformation acting on phi dagger phi, Cp transformation acting on B mu nu, Cp transformation on this guy, and you know that because the point is Cp on B mu nu will pick up a negative sign, and so here, so therefore there will be no change, and the Cp transformation on O phi b remains the same. What happens on O phi b tilde? Now, the point is this operator constitutes of one field strength tensor and one conjugate field strength tensor. So, the Cp transformation will have a sign here, no sign here, no sign here. So, there will be a negative sign here. So, therefore, these operators will be Cp odd, like those which will involve B mu nu tilde. So, this is the conclusion. So, these operators, this kind of operators are Cp odd operators. Are these the only one which are Cp odd? The answer is no. These operators which involves the field strength tensor and its dual, and they are showing Cp violation as we just discussed. But on the other hand, this kind of operators, because they can involve complex Wilson coefficients, from that part you can induce imaginary parts in these operators, and they will also provide you CP violation. So, therefore, these kind of operators are classified as CP odd operators, which will affect the Higgs physics. Now, this is an interesting, so once again I am not going to remind you, so the coefficients are named essentially, so these are the Wilson coefficients which sits in front of all these dimension 6 operators. So, what one can do, that one can go back and look up a particular process that interests you, like for example Higgs physics, and you see that these are the class of operators which will affect some observable or the other related to Higgs physics, and this I am actually copying from one of the paper of Maltoni et al. And similarly, you look for die boson production, these operators will come into play, TT bar vector boson, this set of operators will come into play, and so on and so forth, top EW, etc. And some of this will contribute to electroic precision observables, TT bar production. So, these are all relevant processes which LHC is now looking into, and this Wilson coefficients, that means those corresponding operators will actually contribute to this kind of observables. So, let me get back to the Higgs coupling specifically. For example, I mean, let us think of the vector boson fusion process, ZZ Higgs. Now, it is not very difficult to kind of expand this operator like H dagger d mu H star, H dagger d mu H, and if you expand this, which has this coefficient named like CHDD, I mean my conventions have been different because I am copy pasting from different places, I apologize for that, but never mind, but you can show that this will actually give additional contributions to the ZZ Higgs coupling to the one which is existing. So, therefore, the presence of this kind of dimension 6 operators will give you additional contribution to the ZZ Higgs coupling, and so if you have any ifs and buts in the measurements of Z Higgs coupling, you might think there is a contribution which is coming from this kind of dimension 6 operators. And this exercise can go on for other operators also, like H dagger H, G mu nu will produce an additional contribution to glue Higgs, etc. And this exercise can be extended for all these different operators involving the Higgs field that we have written. Yeah, so I am not repeating further, but you can see that this is the list, and one can verify, for example, QQ2 TT bar. So, there is an interesting part, this slide is important, because suppose you want to produce TT bar Higgs at the LHC. So, you may think that those operators are only contributing, those effective operators can additionally only contribute which has explicitly the Higgs in it, but the answer is no, because in that process you also have a graph where you can produce via ZTT bar, and this vertex ZTT bar that can get additional contribution from this vector current interaction operators. So, that will give you additional contribution to finally TT bar H production also. So, therefore, when you are trying to extract the TT bar H coupling, it is not only those which are explicitly affecting that Yukawa term, but also the other processes or the processes which involve the production of TT bar, etc. So, all those things have to be taken into account. I will give you an explicit example in the next slide, and this is the example that I have at hand. Let us consider the Z Higgs production mode. So, within the standard model we have ZZH production and or gamma ZH. I mean, in principle this channel is not there, but when you include the effective field higher dimensional effective operators into it, then This is the standard model contribution, and then these are the bunch of additional contributions that actually you can get from these operators. Like you can get additional contribution to ZZ Higgs coupling, you can get an additional vertex like Z gamma H from these operators. This is a 4-point interaction that can be generated by these operators, like having this. Once again, I mean, you have to just go back and see the nomenclature, what is O1 HQ, what is O3 HQ, but those will actually generate this kind of 4-point interaction which is not there in the standard model. And similarly, you can also have additional contribution to QQ bar Z coupling via these effective operators. Okay? So the point is, when you are calculating your ZH production at the LHC, on top of the standard model, if you take the contributions from these higher dimensional effective operators, then all these different diagrams will actually contribute. Whether they will interfere or not depends on their CP nature, etc. But this, all the other graphs one has to actually consider. So, for example, O1 HQ is this particular operator, which you can check that once you expand them, they will give you a contribution of this sort, including this one. Okay. There is one interesting point that we would like to know, note about this contact interaction, because you remember that in the standard model you have the S channel propagator, but there is no propagator in this one, and this is a contact term. And interestingly, this matrix element, if you calculate, will be independent of S, or no S channel suppression for this EFT diagram. And if you want to write the Feynman rules for this kind of graph, this will show something like this, with this coefficient of C1 HQ by lambda square. And remind you that the standard model contribution, which is this S channel Z mediation, actually has a suppression of 1 by S. So this is the point which Jose was mentioning, that due to the presence of this kind of effective 4-point interactions which does not have a S channel suppression, the cross section actually can grow when you take this contribution into account, and particularly if you go beyond the effective theory limit, this can give you a violation of unitarity. So therefore, it is important that when you take such kind of contributions into your calculation, you must obey the effective field theory limit. What that effective field theory limit is in context of this Higgs production at LHC, we will just talk about that in a moment. So now, if I just measure the cross section and plot the distribution in terms of what is called the invariant mass for the production like Z Higgs. So I am considering this production like PP going to Z Higgs, and what I am defining here is a variable called the invariant mass of the final state, which involves the momenta, 4 momentum associated with the Z boson, the 4 momenta associated with the Higgs boson, and the square of it, and when you take the square root, this what gives you the invariant mass of the final state. And this is an observable which you can actually cook up with the final state signals or the number of events that you actually see, subject to the fact that how well you can reconstruct the Z and the Higgs depending on what final state that it is decaying to. But this is an observable that you can in principle see in association with the ZH production. Now, when you plot the event distribution with respect to the ZH, so when I just had the standard model, the distribution was something like this in the blue curve, and when I had the standard model plus the effective operator inclusion, the invariant mass distribution of the signal actually has changed a little, and this is what it is. So there is one interesting point to note first, that the effective operator contribution is actually coming to the higher invariant masses, right? And the reason is once again the one that I just pointed out before, that the 4-point interaction that contributes to this kind of ZH production in the effective operator context is not there in the standard model. In standard model, it is the S channel separation. So, when you include this effective operator contribution, in the tail of this ZH distribution, there is an expectation that this effective operator contribution can show up. I think this is simply because of the fact that we normalize this to 1, the cross sections. This is a normalized distribution that we are plotting. So, EFT really shows up in the tail, but the question is whether you can enhance the tail to the extent that you want. The answer is actually no, and that once again comes from that warning that you better obey the effective theory limit when you are actually calculating these cross sections, including the effective operators. And so therefore, there must be a cutoff that says that your lambda must be greater than the invariant mass of the ZH. Now, why invariant mass is the important quantity which defines the effectivity of effective theory that we are taking into account, because you see that in a sense, because you are producing Z and H, so the 4 momentum added and squared and taken the root is essentially depicting the energy at which this reaction is taking place. So, in a sense, the invariant mass is the quantity which depicts what is the energy at which this reaction is taking place. So, therefore, once you restrict yourself to this limit that your invariant mass must be less than the lambda, and here we have taken lambda equal to 1 TeV, and that is why you see a cutoff here. This says that you are well and good and you are respecting your effective theory limit. Okay? So, this is important while you are doing this kind of searches, and this marks the validity of the EFT regime. I will also give you another example which is about the vector boson fusion production mode, and in the vector boson fusion production mode, so this is the standard model graph that you actually have once again, but when you take the effective operator contribution, the contribution actually come from the modification of the Higgs gauge boson coupling via the same operators which we just talked about. You can have the effective operator contribution affecting your this particular vertex like Q, jet and the gauge boson, as well as you can have an additional contribution of Higgs coming out from this particular graph. So, there is nothing to worry if you do not see it from this nomenclature right now. It is just that you have to take that operator, take that unitary gauge expression for the phi, expand the operator, see where exactly the vertices are contributing, and you will be able to see that there are additional contribution to this vertex, or there is a new vertex which you are finding through these channels. And yeah, once again this operator comes into the play like H dagger H W mu nu tilde W mu nu here, which you remember we sort of said that this is one of the CP violating operators. So, there is a CP violating operator that is contributing to this particular channel. So, now the question is there a way that we can probe the CP violation, and what we can do. So, this is the reaction, say let us for example we are taking this graph and you remember that this is the vertex where the contribution is coming from that CP violating operator using the field strengthener and its dual. And so, these are the 4 momenta associated with this thing, and then you define the kinematic variables like the transverse momentum of the final states of the jets and the Higgses, etc. And this is an interesting variable that we define, which is the phi, which is tan inverse of Py by Px. Now, the question is, can we construct a CP odd observable in this process? Now, the CP odd observable can be epsilon mu nu rho sigma k mu k prime nu q rho q prime sigma. Now, what exactly is this thing? If you expand this, it can be written in terms of 2 e prime q prime cross q dot k, where all these are the momenta associated with the initial and final states. Once again, this is a parton level thing that we are saying. In order to reconstruct this momenta in context of a collider, one requires to do a bit of hard work. And it is not very difficult to check that this relation comes from this construction using this triple product of vectors A cross B dot C is equal to epsilon A I j k A I B j c k. And if you do a couple of steps of this calculation, then you can show that this quantity actually transmits into something like 2 E E prime q t prime sine of delta phi j j, where delta phi j j is nothing but the separation of the angle of these two jets which are coming out. And so therefore, this observable, if you construct, carries the imprint of CP violating Lorentz structure that is contributing to this kind of a production. So, this is an interesting direction that one can also look up. And if I plot the delta phi j j distribution once more with normalized events, my apologies to Anupam, and then once again we see that this blue line is the actually one which has the standard model contribution, whereas the one in the red is the one which has this additional contribution of this CP violating operator. So, therefore, there are ways of distinguishing or rather seeing the effect of these different higher dimensional operators contributing to your different production modes associated with the Higgs, and infer whether they whether they can I mean what you do now, that because we have no excess in any of these channels beyond the standard model, what people usually do, that they put limits on this Wilson coefficient by the lambda square. But we all know that LHC is going to be operational for higher luminosities, and where we will have many more data, much more data, and there is a possibility that these effects, however small they are, can actually show up. So, there is a possibility of distinction between just the pure standard model and standard model plus effective operator contributing to this kind of productions. This one, right? Yeah. No, this is the specific thing, that because we had the CP violating operator contributing here, that shows up in terms of this delta phi j j, and there is a contribution which is coming up from this 2e, the transverse momentum, etc., and whatever that was sine of delta. I forgot the formula. Let me go back. Yeah, sine of delta phi j j. So, this is specifically due to this particular way that the contribution of the CP violating operator is I mean, so the separation angle between the jets can be a good observable to distinguish between the standard model and standard model plus effective operator contribution via the CP violating contribution. This will be falling, yeah. So, the maximum is actually when phi j j is equal to 0, right? I mean delta phi j j is equal to 0, that is they are actually collinear, and then as you separate the angle more, the contribution drops. But here for this particular case there is a peak, yeah, with this inclusion of the CP violating operators.
So in your earlier example, so you consider
This one, example 1, right?
So my question is the same
Yeah.
Wilson coefficient, the same operator.
Yeah.
So can also get constraint from B physics. Let's say.
Absolutely, absolutely.
So
Yeah.
whether that will affect this.
Of course. I mean, see here what you are saying that you have chosen a scale lambda, but this Wilson coefficient that you have chosen here is usually order 1, that is what we are saying. But whether that is consistent, if this operator contributes to other flavor observables or other low energy phenomena, that has to be taken into account. So when you choose your C by lambda square together, it is to make your calculation consistent, you have to see whether there are other contributions that this operator can contribute to. Say for example, you are saying that if it is contributing to some flavor violation or something, that has to be corroborated, and depending on how large or how small that C is will definitely alter the visibility or the distinguishability of the contribution of the effective operator, for sure. I mean, if you blindly take C equal to 1, which we are taking here just to show as an example, but in a careful analysis you have to take into account those kind of other constants, and that will definitely say how large the feature will remain the same, the pattern of the plot remain the same, but whether it is inflated or it will be subdued depends on how large this Wilson coefficient is.
Thanks.
Yeah. Okay. More questions? Okay, let me get back to my last slide. Yeah, so the last point that I had to say is, remember that this distribution that I have showed is only signal distribution, and signal distribution coming from the standard model, and the signal distribution coming from the standard model plus effective operator. But life is not that simple. There are huge standard model background contamination which is going to affect your observable. Like say for example, you take TT bar contribution, that will contribute to, suppose you take ZH production, Z going to L plus L minus, Higgs going to B bar. There are many processes which has nothing to do with the ZH production, but will produce 2 leptons of opposite sign, 2 BJs in the final state. If you have to, if you want to do a realistic analysis, you have to take all those contributions seriously. And if you take all those contributions seriously, the first question that rises is the distinguishability of the signal itself. The distinguishability of the signal and the distinguishability of the signal coming from the standard model plus between standard model and standard model plus effective operators comes next. The establishment of the signal over the background fluctuation is the first important point, and there it is not very easy. So all these nice features that we just talked about is subject to the signal discovery over the background contaminations, and this is where there are these recent machineries which are being used to segregate the signal and background distributions via this machine learnings and deep learning techniques, which many of you I am sure are working upon, and so this is going to be a great help, so therefore for a realistic analysis we have to take everything together, the signal plus effective operator plus standard model background. Do choose event distributions or event variables or final state variables that discriminates your signal and background to the best extent. Use those to fit into the machine learning tool that you are using, and they will choose a combination of those variables which actually segregates the signal and background best. I mean, just you have to know how to do that, and once you do that, then you ask the question, can I now distinguish between the pure standard model contribution and the standard model plus effective operator contribution. So this is the procedure by which a realistic calculation proceeds. I think we have also a talk by Shankho, so who is going to talk about more on the Higgs physics and its searches, including the effective operators in context of LHC and in particularly with higher luminosities. So, stay tuned for that, and I will finish here. So, we are finishing early, that is not a crime. I think we have a photograph session also. So, yeah, okay, thank you so much. More questions if you have. Tisha, someone should give her a microphone. Sorry. She is an expert, yeah.
I am asking that in the background there can be contamination from other EFT operators
absolutely. Also. Yeah, that shows that she is a practitioner. So, yeah, you are absolutely right that it's not only the effective operator contributions to the signal, but when you take your effective operator series as a base for your signal, then you also have to take that into account for the background searches also. You are absolutely right. Yeah.
So, in that case, studying just one observable is not sufficient, right? So, we need to take more observables into account to distinguish between the EFT operators also.
Absolutely, precisely. Yeah. So, one observable will not be. So, we are not talking about those how you can extract or put limits on the Wilson coefficients because that would be a little complicated, at least for this lecture I thought, and also I was not prepared. So, that is the second point. But you are absolutely right that when you are putting bounds on your Wilson coefficients divided by lambda square, because you in principle can't segregate between these two at this moment, then you have to, it's better that you take like vector boson fusion, Higgs-Stralholm put together, and then you will be able to see the distinction, or rather put a consistent bound on those kind of because they will contaminate all those signals that you are seeing. So, it is better that you do not choose one particular production mode and a particular signal mode, rather you look for all those different cases and put the bound together from all these different observations. Yeah, absolutely.
Can you go on the slide where unit mass for G Higgs?
Correct. Yeah.
Okay, so here in the tail, so the red plot, it is for EFT, right? So it is for 1 by lambda square contribution. That means 6-dimensional operator is contributing significantly, right?
Yes, yes.
Okay. So when we write
subject to the C value, which someone asked that what is the C value, we are taking C equal to 1 just to show you a nice distinction, but in reality if you have to take contributions from other observables which restricts your C by lambda square, then if you take a smaller value of C, it will not be this prominent. Yeah.
So here in amplitude square we will have 1 by lambda square into standard model interference.
Absolutely.
Then we will have 1 by lambda 4 in a
correct
quadratic. Okay. Then we should have contribution in principle from 8-dimensional operators.
Absolutely. So in cases, this is a very important point that you raised, particularly for those operators, those in particular which is CP odd, they do not interfere with the standard model. So if you are taking the CP odd observables, because it will be perhaps helpful if I just write one line. So in a sense you are saying that this is MSM plus MEFT, which is like supposedly whole square, and so therefore MSM square plus lambda square plus, right. So there are cases, I mean whenever this interference term is present, depending on how large your contribution or contamination is, you have to decide whether you take also the contribution from dimension 8 operators. But if it is not there, then perhaps it is imperative that you have to take those higher order corrections. Yeah. Well, in that case also, I mean, this has a caveat, because if you take the dimension 8 operators which are CP violating at the same time, they will also not interfere, and they will come even at the 1 by lambda to the power 8 order actually. So, but yeah, in general your comment is right, that depending on how large this contribution is, you can decide upon whether to include this or not.
So by this plot, it seems that the quadratic is contributing more than the interference.
This is yeah, you are in a sense right, because this is mostly coming from this graph. I mean,
yes.
whatever. Yeah, you are right. You are right. Yeah. So, yeah, you are right. Yeah, that is because we are just taking this C to be simply order 1 and lambda equal to 1 TV to show the case. Yeah, you are right. So, this contribution is predominant in this particular case. Yeah, true. I mean, the distinction in the tail that you are showing.
So, in that sense, dimension 8 operators are also important.
It's blindly neglecting that will be difficult. Yeah, true, true. Yeah, life is complicated.
One more, the delta phi distribution.
Yeah, yeah.
So in PP collider, we can make we cannot make genuine CP out observables like we do in lepton colliders, right?
True.
Because we have PP means composite PP
Particles, yeah.
So we cannot do that, but is there any way, like you have shown in the
previous slide, that the separation between the
just by kinematic structure of the operators.
Yeah.
So is it hard to do always? Means always we cannot do that, right?
So your question is how legitimate?
We cannot construct always
a CP violating observable.
Yeah, just by looking at.
True. So in principle, the argument for the previous slide was the following, that see, ultimately these are measurables, like energy of E and E prime are essentially this K and K prime, the initial, well, I mean, so, and this transverse momentum associated with the jets, these this can be sort of measurable. So that's what we argued, that then perhaps this delta phi j j will have the seed of the CP violation contribution to this kind of to this production, but you are right. I mean,
although this is sign sensitive, means if you flip J by J1 by J2, but we cannot do that in diazide production in LHC.
True. True. Yeah, it's a very naive calculation. I mean, it ignores or undermines several important observable possibilities or consequences, as you are pointing out. True. Yeah, agreed.
So can we understand? Can you go on the delta phi distribution?
Yeah.
So, so in PP collider, the jets are very forward, right? So they are like back to back.
Absolutely.
So that's why in standard model delta phi is around 0.
Absolutely.
Or if you look at if your delta phi goes from minus pi to plus pi, then it will be like symmetrically means peaking at 0, so peaking at minus pi and peaking at plus pi.
True. This kind of a distribution, yes.
And there will be no events around delta phi equal to 0.
Exactly.
It is here because it is
more. Yeah, there is a delta phi jj contribution.
Okay, so,
yeah.
Then, so somehow if you look at delta phi jj equal to pi by 2, that means somehow beyond standard model physics is pushing one of the jets or angle between the jets around pi by 2.
True, true,
And
absolutely.
Yeah, that we can understand from that structure which has PT.
PT, exactly.
Right. So once you have delta phi around pi by 2, you will have
large contribution coming from essentially sine 90 degree equal to 1.
Right.
Sine, yeah, absolutely. Yeah, that's very nicely elaborated. Thank you. Yeah, that's very nicely explained. So what he is saying that just the contribution, if you look into, which is actually sine of delta phi jj, so that will give you a peak at delta phi jj equal to 90 degree. So that's what it is showing. That. Yeah. Any more question? Shobit.
Yeah. So in this red line, so is there only this CP odd effective operator is considered?
Yes.
But there might be, I mean, other CP even operators in that dimension.
Absolutely.
So if we consider that, how this?
Yeah. Well, the answer is I don't know, because we have not done the calculation. So, or rather, we can do the calculation. I mean, it's not very difficult, but this feature will be there. So, this is the distinguishability that we wanted to show due to the inclusion of CP odd operators.
So, those CP even operators that won't be depending on this delta phi jj?
That will not give a distinguishability in this regard. So, you know, you will inflate the structure, or, you know, depending on what are the other combinations that you choose, you may not retain this beautiful structure as we have here. Yeah.
Okay. Thank you.
Yeah. More questions?
Yeah. So in the standard model, we don't have direct coupling of Higgs and gluons.
Yes.
But here in the effective field theory, there is I saw a vertex that Higgs
you
to
can. G mu nu A, G mu nu
A. Then what will be the structure of the coupling constant? Because in the standard model, it's a loop induced thing, and here you are writing in the
Jose is going to do that for you, not in general for the gluon, but he is going to argue that there are a class of operators which cannot be generated at the tree level, and those are what are called loop generated operators. And when you include the field strength tensors in particular, like that you pointed out, that can be shown that that can only be generated at one loop. Now, what new physics that can generate that requires a bit of, you know, I mean, you have to look into that, but the G mu nu H dagger H operator is certainly one of those new, some of those what is called the loop generated operators, and which will have an additional suppression of 1 by 16 pi square. So, in principle, if you take the coefficients, Wilson coefficients having the same order as those of other operators which can be generated at tree level, which he will mention as a potential tree generated operators, then the calculations are not completely all right. So, this is something, because then it will be saying that you are taking the Wilson coefficients 100 orders more, that if you take the C of the order of 1 for loop generated operators, because it has an inherent 1 by 16 pi square sitting downstairs, then you are basically inflating it too much, and that goes beyond the weakly coupled new physics system that we are generically talking about. So, there are bit of caveats. So, you are absolutely right that these operators cannot be generated at the tree level, and this will only come at the loop level. Okay, if no more questions are there, then we can finish this session, and I think we have a photograph session right now. Okay. Thank you, thank you. And so we can have the photograph outside. Where exactly we have, Ovik will tell us. Top.
এই যে
যে এই যে ওরই পাশে যে সিঁড়িটা আছে এখানে নিচে হয়ে যাবে জানো ব্যাপারে হ্যাঁ কথা বলছি ওই জায়গাটা যে সিঁড়িটার তত্ত্ব 230
নেক্সট স্টেপটা হচ্ছে যে তোমার বেসিক্যালি আমরা যেটা করেছি সেটা হচ্ছে যে মানে c বাই ল্যামডা স্কয়ারের যে লিমিটটা সেটা মানে এখন দেখো তোমার কাছে দুটো পসিবিলিটি থাকতে পারে তোমার কাছে মিন বাই মিন ডিস্ট্রিবিউশনের অবজারভেবিলিটি থাকে তাহলে সেখান থেকে তুমি ইচ বি তুমি ভাগ করে দিবে এবং সেখান থেকে তুমি বললে আচ্ছা এই দিনে এইটা চলো আমরা ছবি তুলি মানে আমরা section that we want to pick up and option. Yeah, I was particularly happy with the comments that you actually made for us.
So actually, my work is related to culture. I have not worked on computers, but I do model from here. But I have not worked on.
Oh, you have.
Yeah, I construct MMO statements.
Okay.
Can you tell your friend from?
Yeah. Is there something interesting there? Yeah, there are n number of forms that we have to fill, and keep them back because no. That's the reason. No, no, no. That's not. It's more important that you ask. So I will escape for half an hour. Go and do that stuff. Start with the forms. Yes. Once I yes, exactly. I will tell you sign here.
Okay, so good afternoon to all of you. Before we start this session, I have one announcement. So the announcement is as follows, that today after the guest lecture by Satya Narayan, which will be during 4 to 5, we will have an informal session with all the participants where we want you to kind of tell us your name, your affiliation, and the kind of things that you are doing or interested in doing. Okay, so be there, and it will be very good for us to actually know that also. Yeah. Okay. So thank you.
All right. So, hello again. So earlier today, this morning, I ended up at the beginning of what I was calling the equivalence theorem. That's the general name. And this is the proof that if you have two operators that satisfy a relation like this linear combination, which vanishes when the equations of motion are applied, if that should happen, then what the theorem shows is that the S matrix depends only on this linear combination of coefficients. And instead of going straight away to the field theory part, then I will go and do an example in quantum mechanics, which I think might motivate the thing. All right. The example is straightforward. So what the theorem says, I should say, the theorem says then that if we have an object that looks exactly like this, a phi like this is an operator. If we have an operator that looks exactly like this, then it should have no effects at all. This is an equivalent, sorry, well, this is an equivalent statement of the equivalence theorem. So if you have an operator like this is an operator, the same dimension as O and O prime, and this operator you put into your effective theory, this operator will have no effect. That means this S matrix will have no dependence on the coefficient of this operator. It will be independent. And that's what I'm going to look at. So this is my theory. It's a very simple non-relativistic quantum mechanics in one dimension. The x is the coordinate. And what I'm adding to it is a term that vanishes on shell. And on shell is exactly the definition that I just gave you, that vanishes when the equations of motion are obeyed. And I'm using more or less the same notation. A represents this curly A, and this variation here in one dimension quantum mechanics, in one-dimensional theory, is exactly this. You derive this from this. One can easily rewrite this by making an integration by parts in this part, so that the Lagrangian depends only on the velocities and not on the accelerations. And you get this. The momentum, the canonical momentum, you get by taking the standard expression, taking a derivative of L with respect to x dot, and it's this object that again depends on the effective operator that I added. And I forgot to mention, so I introduced an expansion parameter. I mentioned that I'm working to leading order. In this case, it means leading order in epsilon. This corresponds to 1 over lambda squared expansion, and this would represent these terms would represent the higher terms in the effective theory. I take this, and using this expression, I can construct the Hamiltonian. This is the standard expression of Hamiltonian. And if you work it out, you get this object. This is the standard thing you would get from this Lagrangian immediately. It's straightforward. And this is an extra piece that comes from adding this extra piece. And I will call this extra piece H prime. I'll call this thing H naught. Now, if I want to quantize the theory, I can, of course. The only subtlety occurs on this term because of an ordering problem. If A depends on X, and so whether you have A prime PP or you have PA prime P or PPA prime, quantum mechanically as operators is different. So what I will do is choose an ordering so that the operator, the Hamiltonian is Hermitian. I will just impose that. I will choose that ordering, which is equivalent to doing this. The curly brackets denote anti-commutator, or equivalent. This is the symmetric ordering with all possibilities. P squared A prime, P A prime P, A prime P squared. And if you substitute this thing that I had here in here, well, you get an expression for H prime as an operator, which is here in the parentheses. And what is interesting is that this full expression for H is just a unitary transform of H naught. So there's a unitary matrix explicitly presented here, that if you calculate this thing to order epsilon, you get exactly this. So there's an identity. I remind you the thing in here, the P squared plus V, is what I call H naught. And then when you dagger at this thing, it's a unitary transformation. So the theory is unitarily equivalent. The theory with this is unitarily equivalent to the original theory. So the theory with this Hamiltonian, corresponding to the Lagrangian with an epsilon term, is equivalent to the original Hamiltonian, because unitary transformations are free for you to do. And it is in this sense that an operator that vanishes on shell in a quantum theory, it has no observable effects. You can make a unitary rotation, and then all the effects of this term in the Lagrangian or the Hamiltonian disappear, and you're back with what you had when it was not introduced. What does change are the canonical coordinates, okay, like this, and you can work out all observables. But that's basically at this level the equivalence theorem. Right? We added a modification that looks highly, or can be highly non-trivial to the Lagrangian, and yet by virtue of its vanishing on shell, it is in fact an unphysical modification, and an observable modification. Any questions about this example? Doing this exact same procedure at the quantum field theory level is not feasible. Well, certainly it's feasible. It just requires too much background material. I would have to introduce the Schrodinger picture in quantum field theory, which is doable, done, but it's very, very rarely taught. So you're very unlikely to be familiar with it. And so I will not go through the same, I will not follow the same approach when I do quantum field theory. But I did want to bring it up because this is what's going on. We added a term, and we can eliminate it by doing an appropriate unitary transformation. If you want to do the classical theory, that's perfectly okay. The only difference is that instead of doing a unitary transformation, you do a canonical transformation. An appropriate canonical transformation will get rid of this thing. And the generator for such a canonical transformation is essentially this object, P times A. Well, then let me move on to the quantum part, quantum field theory part. I'm not going to worry about, okay, I will sketch the proof. I don't want to go into painstaking detail about all possible issues with divergences and so on, but I will mention as I go along the main pitfalls that you might encounter. So I'm going to go back and look at my effective theory, and now again we have two operators that to leading order are related by the expression that I had before, and that unfortunately I did not write down here. So these two operators, O and O prime, are related by this expression here at the bottom. So let me put it on the board. All right. The idea is to put your theory inside a functional integral and then to do a change of variables, or what's often called the field definition of this form. I shift the field by the expansion parameter 1 over lambda squared, if you wish, C prime. I'm going to, okay, so what I'm looking forward to is getting rid of O prime. And I can do exactly the same approach and get rid of O, but I will do the O prime. And so E C prime times A, and A is this A here, okay? Then if you do this transformation upon the Lagrangian that you have originally, you get this expression here. And I note that I've chosen this coefficient cleverly enough so that this combination right here, by definition, can be written in terms of O. So you have this expression O. And you may say, well, now I'm done. I'm done. You just made a change of variables. Then with the new variables, then you have shown that the effective Lagrangian doesn't depend on C and C prime separately, but only on this linear combination. We're done. But it's not quite the case. There is a little bit of subtlety, because whenever you make a change of variables, you have a Jacobian in the functional integral. And here it is. You have to change the measure by Jacobian. The Jacobian is the determinant of the variation of the, you vary this with respect to phi, and you take the determinant of that, and that's your Jacobian. Okay, great. And I'm working to order epsilon, and so you get determinant of 1 that comes from the variation of this guy, and then a variation of A. And you have 1 plus something, and I'm going to work to a leading order in epsilon, and so the determinant of 1 plus small is equal to 1 plus trace of small, which is this. And I will call this the Jacobian. Okay. Now, if you notice, everything here, the operators I've been telling you, are local. They depend on the field at one point, or the derivatives of the field at one point. This is local, this is local, this is local, and therefore the curly A is local. It depends on phi and the derivatives of phi at one and the same point. So when you take this variation, you find immediately that this is full of derivatives or of delta function, or the delta function itself, evaluated at 0. But you are fearless quantum field theory practitioners, and you know that that what you have to do is, before you throw up your arms in despair and leave the room, that you have to regularize things. And which regularization you use, well, it's up to you. But if you decide to use dimensional regularization, what happens in it is that this type of divergent object is 0, regularized to 0. And that's okay. But what if you don't like to use dimensional regularization and really uncomfortable about these things? Well, that is also okay, because in general what you find is that the things that multiply this delta to the 4, the objects that multiply this this operator. So for example, A can have a term that's polynomial in phi, say phi to the n. When you take a derivative of this like this and take the trace, what you get is a delta of 0 times phi to the n minus 1. Okay. By the construction, and that's not something I'm going to prove, what happens in this calculation when you don't use dimensional regularization is that the thing that multiplies the object involving the fields and its derivatives that multiplies delta function at 0 and so on, they are all can be absorbed in renormalizing the coefficients of the light theory. So they are renormalization effects. But if you use dimensional regularization, you don't even have to worry about it to begin with. All right. So the Lagrangian depends only on this thing. I've swept, as we do in renormalization, the divergences that show up here under the rug. And there's one thing left over. And that is where part of the physics comes up. When you do a functional integral approach to finding all the correlators that you're interested in, you end up with a generating function that depends on some current that I'm going to call eta. That's a current eta. And you have an expression like this, e to the is, and then you add a source term, eta phi, so that whenever you want to, to obtain a correlator, well, you just take derivatives of zeta with respect to this external source, and then eventually set the source to 0. So in the expressions that I've told you, I've dealt with this guy. Concerning this guy, I've shown that it depends only on the combination C plus AC prime. But what I have not done yet is talk about what happens to the source. When I replace the field like this, there's the field like this, then I have to do it everywhere. So now I have plus epsilon C prime A here. And you say, well, okay, fine. So now when I take derivatives with respect to eta, it doesn't bring only a factor of phi, but brings a factor of phi plus unwelcome friends. But in fact, those unwelcome friends are harmless whenever you calculate S-matrix elements. The reason for that is that there are two possibilities. One is that A has a term or more terms that are linear in the fields. I'll come to that in a second. But there's another possibility that A has more terms that have more than one field in it. Phi squared, phi cubed, phi d mu phi, phi box phi, whatever it is. Right. Those terms are harmless when you calculate the S matrix elements, because I remind you, to calculate the S matrix, you take your favorite diagram, you get all the external propagators, then you ruthlessly amputate them by multiplying by the inverse propagator, and then you set every single external line on shell. If you have an external leg, that's what happens when you bring down this factor, including an A. So if A has more than one field, the external leg corresponds to more than one field. And so it will have no single particle pole. When you multiply by p squared minus m squared, inverse propagator, the amputation, it doesn't cancel anything in the denominator. There's no such thing in the denominator because there's no single particle pole in A. And so when you set the external legs on shell, those terms vanish. And that is why this is the dependence, that's the dependence of the theory only on shell, only for the S matrix, only for observables. If you don't do that, you just calculate the endpoint correlator, which is something you can calculate, then the dependence on C prime does not disappear. You know, you bring down n powers of this object over here, and there will be n phi's, and there will be at least one inclusion of A multiplied by C prime without the C, independent of C. But those terms, the ones that depend on C prime by itself, disappear on shell. And there's one last remaining point. It's when A has a single particle pole that is linear in phi, or has a term that is linear in phi. So you have 1 plus epsilon C prime phi, the whole thing. 1 plus epsilon C prime times phi. That case is also not problematic because the factor 1 plus epsilon C prime can be absorbed in a wave function renormalization. And with that, it's a long story, but I tried to be as precise as I could, then the theorem is, I wouldn't say proved, but I hoped argued convincingly for. 3 steps then. Make a field redefinition or a change of variables. In that case, this piece, the S, is shown to depend only on this linear combination. Any effects from the Jacobian renormalization effects, any effects from the shift in the sources can be absorbed either in the renormalization transformation or are irrelevant for the purposes of calculating the S matrix because they don't generate single particle poles. And that is the equivalence theorem. Okay. Any questions? Okay. So let me go on and try to provide an illustration. Of course, I provided an example of how that works. I'm going to work it out also here. And you in the back cannot see this, right? Am I right? Okay. I'm going to try to deal with this. Ooh, wait, I can do this. Make it bigger. Okay. This is as big as it fits. Okay, so I hope you can see this. All right, excellent. All right, so I am going to look at an example of the phi to the 4 theory. This squiggle here is intended to be a 4. So this is not like 1 exclamation mark, but it means 4 factorial. Okay, so this object here is 24. This object here is 2. So it's 1/2 d phi squared minus 1/2 m squared phi squared minus 1 over 24 lambda phi to the 4th. My symmetries. I have a Z2 symmetry. I want the light symmetries that the theory is going to be invariant with phi goes to minus phi. That's why I don't have a phi cubed term here. And Lorentz invariant. That's it. Those are my light symmetries. I only have one field. And so the operators are of the form O 2 to the n, 2k, and the dimension is n plus k, actually 2n plus 2 times n plus k. I forgot the 2 here. The smallest dimension that is not included is relevant dimension operators correspond to n plus k equal to 3. That is dimension 6. I'm sorry, I missed a factor of 2 here. This should be 2 times n plus k. So the smallest dimensional operator corresponds to n plus k equal to 3, and here they are. And what I'm going to show is that all dimension 6 operators are equivalent to phi to the 6. And so this is just a more careful presentation than the one I did earlier today. Okay. So these are the operators that I have. These are the equation of motion. The equation of motion. And so, for example, I can write this operator like this. What I mean by this plus EOM is the following, that if I transpose, this squiggle here is a 3. So if I transpose this to the left-hand side, you get 5 cubed times box plus m squared phi plus 1/6 lambda phi cubed, which is phi cubed times the equation of motion. So the difference between this guy and this guy is a term proportional to the equation of motion. That's what this EOM means. EOM means a term like this here on the board. And so what does the equivalence theorem say? Well, the equivalence theorem says that I can replace this operator in the effective theory by this guy. And this guy has 2 terms. One of them is minus 1/6 lambda phi to the 6. Here it is. And the other is a term that's phi to the 4 m squared. So the effective Lagrangian will have, if you replace this, c prime over lambda squared times this, plus c prime over lambda squared times minus m squared 5/4. The last term, and once proportional to n to the 4th, can be absorbed in a finite renormalization of lambda. So instead of lambda, I have lambda minus m squared over capital lambda squared phi to the c prime. And so the equivalence theorem tells me that the effects of this guy and the effects of this guy are the same. You can do exactly the same thing for the other guy. This. In this case, you can show, I'm not going to go through this thing, you can do the same, play the same game, that this is the same, can be replaced by lambda squared over 36 phi to the 6 plus terms that vanish when the equations of motion are imposed, plus a renormalization of both lambda and m squared. So when you do the same trick of replacing boxes by this type of object, then you end up on the right-hand side with terms that go like phi to the 6, which is this, terms that go like phi to the 4th, which are eaten up by renormalizing lambda, and terms that go like phi squared, that are eaten up in renormalizing m squared. And so what we're saying is, what this is saying is that the theory, the underlying theory cannot differentiate between the 2 operators, box phi squared and box phi times phi cubed, and the phi to the 6 operator. So the most general, leading in 1 over lambda, effective theory is right before your eyes. Just 1 unknown coefficient instead of 3. On the one hand, you say, well, 1 to 3 is not a big reduction. Right? On the other hand, if you decrease by 33%, to 33% of the original number of unknown coefficients, it's very nice. So instead of having to make 3 measurements to see if you have new physics, you only have to make 1 measurement. Any questions about this? This is intended to be a straightforward calculation, but I'm prejudiced. Questions? Yes? Hold on, here comes the microphone.
Oh, okay. So hello. Effective operator can never be equivalent to the low energy any other operator, right?
Well, at low energy, these are equivalent. But
No, the theorem is for 2 effective operators, right?
Yes.
One of them being effective and the other one being
ineffective.
Right.
Exactly. So what I'm saying is, it is the only thing I'm saying is that if you have a new physics that somehow generates this guy at low energies, and you try to measure deviations from using this theory, you will measure deviations for that type of new physics just as much using this thing as if you had put this guy here. You don't have to put them both. You just need one. Because at low energies, the effect of this guy and the effect of this guy really cannot be differentiated. So one of the things that might be of interest is to see how it works at the diagrammatic level. This is the second part of this calculation. And instead of showing the equivalence of this thing, what I'm going to do is add to my theory this guy, and I remind you this whole object here is is precisely this, the equations of motion, if you wish, the variation of the light theory with respect to phi. This is this. So if the theory is correct, then if the theorem is correct, then changing this, adding this, should not affect an observable, any observable. So I'm going to do and see, check whether that's actually the case. And the headache in this calculation are the combinatorial factors. So this guy, at the level of Feynman graphs and Feynman vertices, has 2 types of vertices. Vertices that have 4 legs, like this guy together with these 4 legs, and vertex that has 6 legs. The vertex that has 4 legs have a derivative. And so what you get is this 6i over lambda squared times the summation. The summation is over the 4 legs. I goes from 1, 2, 3, 4. And m squared is this m squared, and so on. And the operator O here it has a term that goes like 5 to the 6. This gives this object here with this particular combinatorial factor of 5 factorial c over lambda squared. So what I've done is I've added to the 3-level Lagrangian, the renormalizable Lagrangian, I've added c over capital lambda squared times O. I've just added it. And so you have a theory that has these additional vertices. All right. So what I'm going to look is at the effect of having a single insertion of O, according to what I've told you, that should give no observable effect, on a process that has 6 external legs. Okay? External legs. So sample diagrams are this guy that comes from here, and a guy that looks like this with all possible combination of where the legs go. Okay, I didn't write down all these things. This vertex here is the vertex in the original renormalizable Lagrangian. This vertex here in blue is the horrible thing that I showed you before with the momenta and the blah, 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 and the factor of 6 and all those things. And what do you have? Well, this guy, what do I have? This guy here is, okay, let me first go to, oh, this guy gives me this term here, I over 120 c lambda squared. 120 is 5 factorial. So from this guy, I get this. From these guys, I get several terms. Okay? One of them has a single particle pole, like you can see here and here, external. And another term that does not have such a pole. It looks like it is. The p squared minus m squared is, I got confused. Hold on. Oh, okay. So, yeah. There's one term here. Okay, sorry. I'm sorry, I apologize. I need to be moving back and forth. It doesn't. Yeah, I'm just going to make it a little bit smaller so that it fits in the screen like this. Okay. All right. So analyzing Feynman graphs is always very boring, but I think it's a kind of an exercise that might be worth for you to look at. This guy has 4 terms, where k squared minus m squared correspond to each of the 4 legs here, right? When you look at this type of object, there will be one term of this 4 where the k squared minus m squared corresponds to this leg here. And I've labeled the momentum here p. So that term will give me a 6i over lambda squared, p squared minus m squared. And then there's a combinatorial factor. And then there's the propagator here, I over p squared minus m squared. And then there's that minus I lambda that comes from this guy. This is this term. And then there are other terms where the k squared minus m squared corresponds to this leg, and that leg. This is this guy, or these are these guys. Okay? Okay, so now what happens? You are now to take all particles on shell. So these guys all vanish because on shell, the momentum on the particle here is squared, will be m squared. So these guys go away. And these guys cancel. And the headache in the calculation is getting this factor of 20 from doing the combinatorics. I have an explanation here, but in my experience, trying to explain combinatorics is a futile exercise. It kills everybody, and in the end, everybody understands combinatorics and his or her own peculiar way of understanding how things arrange themselves. And so the way I try to understand it is different, considering this field chi and trying to see how many ways I can contract this phi cubed times box plus m squared phi, which corresponds to, phi cubed box plus m squared phi. This would be what I call chi. How many ways I can contract this with a phi to the 4 vertex. And this is the thing that I kind of got, and I got the 20. But I'm happy to to work with you individually if you're really curious about this thing. I think that this is less interesting to me than seeing how the things arrange by themselves, apparently miraculously, so that a contribution from this graph will cancel the contribution from the other graph, while the other contributions from this guy vanish on shell. And so you never get, you get no effect, at least for this particular example, of the insertion of my operator O in a process that has 6 external legs that are on shell. Let me point out that if the legs are not on shell, then these guys do not go away, and you get something. You get something that depends on the coefficient of the operator that I forgot to write down here, but it should go here, C. Okay. You can see this by, there's a lambda squared. I forgot a C here too. But on shell, that term disappears. And so the effective action will simply be independent of this operator O. And you can see this. The virtue of doing it, as in the previous slide, is that you have a general proof. You don't have to do diagram by diagram and calculate the combinatorial factors, which are always rather painful. Any questions? Okay. So the equivalence theorem allows you to eliminate operators. You had an example of how it works in quantum mechanics. You have a sketch of a proof of how it works in quantum field theory, and you have an example of how it works in practice at the diagrammatic level. So I think that's pretty convincing evidence that this is something that's reliable. Sorry, going the wrong way. And now I'm supposed to put it. I can even do this. All right. Okay. And that is the end of this. Any questions? Any questions about anything before? No? Going once? Going twice? Oh, it's all gone. Okay. I'm back. All right. So let me just talk a little, begin. I'm not going to do much. I'm going to finish a little bit early today. I think that's enough formalism for one day. But let me just talk a little bit about the renormalization and renormalization effects of doing this. I am going to talk about renormalization of effective theories. I'm going to argue here finally that something I told you on the very first lecture is true, that the effective field theory in its infinity of coefficients is in fact a renormalizable theory. I will argue that the hierarchy that I imposed using this index is in fact something that's preserved under radiative corrections. That is, if you have leading operators renormalize themselves to leading order. If you include, so in order to understand how the renormalization works of your effective theory to leading order, you don't need any of the subleading operators at all. They don't contribute to that. So that will be interesting, I think, and reassuring. There's one subtlety, but I will cover that. The one thing is whether you can, another question you might ask is whether you can calculate the renormalization group running of these coefficients, the effective coefficients, because it's fashionable. And the answer is absolutely yes. You can certainly write down the running of the effective operator coefficients. The question is, I think, more whether you should do that or not. in the sense that, well, you get anything really, really interesting. And in most cases, the answer is definitely not. No. Why? Because in reality, our current reality is that we are probing the very largest or most interesting standard model radiative correction effects. So there are a very small number of observables that are sensitive, that have been measured to sensitivity so high that we can probe beyond leading order. Okay. This excludes QCD because it's strongly coupled, but I'm thinking of a weakly coupled part, the electroweak part of the theory. So there's some observables associated with the Z boson, which has been so well measured, that you can start seeing deviations from 2 loops. But most of the observables we have are sensitive only to 3 level. A few select ones are sensitive to 1 loop, all within the standard model. And 1 or 2 are sensitive to higher loops. So you might question, and I think rightfully, whether you start looking for radiative corrections, and renormalization group running is a radiative correction of effects that are produced by the effective theory. After all, we have not seen any inkling of the effective theory effects in data. We have only limits. We have no observation. So we know that if there is new physics, its effects are much smaller than the standard model at 3 level for some observables, smaller than the standard model plus radiative corrections in the select observables that I mentioned that are very high precision observables. And so imagining that it will be really useful to calculate the full renormalization group running of an effective theory, I think might be premature, especially since you notice that I've had 59 operators that you're going to look at. That's a lot of loops, a lot of loops with a lot of indices and a lot of combinatorial factors that you have to worry about. And so what I will do here is certainly not evaluate the running, but try to argue for you that the running that you would get if you should want to do the calculation can be obtained by just limiting yourself to the dimension 6 operators of the standard model effective theory. You don't need the dimension 8 operators to the standard to find the leading expression. Okay? So that will be the goal of this section of the theory. So let's stop now. I know it's a little bit early, but I think, again, I don't want to start something when we're all a little bit tired and overwhelmed. And so let's begin fresh tomorrow morning on the renormalization part. Okay? Yes, sir. Hold on. Wait. Please wait. Thank you.
And let's say I have an operator O. Is a CP conserving operator.
Oh, so this operator?
Yes.
Which
O.
operator?
Let's
This?
say O.
Oh.
And is there ever possible that is equivalent operator O prime can be CP non-conserving?
That OP can be CP non-conserving.
Let O be CP conserving and O prime becomes CP non-conserving.
Yes, it could be, because the standard model has CP violating terms. So you could imagine that when you do this thing in the standard, but it will be very small effect, right? Because the standard model has one certainly but CP violating phase in the CKM matrix, tiny effect, and it has a potentially another one in the neutrino mixing matrix phase, right? And so when you calculate this type of thing, there will be, at least for some cases, for choices of phi, there will be some times where this thing involves the CKM matrix, And so the right-hand side will be CP violating, right? For that term. But so there will be a CP violating term. You told me, okay, it's your operator, this is CP conserving, and the only way this can be consistently true is if O prime has a CP violating piece. However, the CP violating piece will be small. Okay, it will be small. Other questions? Yes.
So, in this proof, we said that O and O prime, they will not be distinguishable at low energy effects.
Right.
But can you tell me the scale at which we will get distinguishable effects, like at what powers we will start?
When exactly? So the question is, when can you start distinguishing them?
Yes. Yes.
Okay. Yeah. This can be distinguished if you are sensitive to the subleading operators. That is, you have enough sensitivity. If you bear with me and assume this refers to the standard model effective theory, this would be, say, dimension 6 operators, right? If you are sensitive to dimension 8 operators, then you would see a difference between this guy and that guy. So I cannot give you a number, like if you measure blah, 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 everything, blah, blah. No, I can't. The reason for that is that we don't know that we are sensitive to the dimension 6 operators because, having seen no effect, we don't know what lambda, capital lambda is. We don't know the scale. So when we see that, I can tell you, if lambda is 3 TeV, that's the scale where we'll be able to start seeing deviations between O and O prime. Okay. Other question? Okay, you get 8 minutes extra of actually we get 8 minutes extra of T. Oh no!
So that A parameter can be a dimension full, some quantity can be.
Could be.
So I mean A is a some, O is some other dimension operator, and O prime is.
The thing works. In practice, that's not useful actually, but yes, it could be. So A could have dimensions of mass. Yeah.
Thank you.
7 minutes extra. Thank you. I will see you tomorrow.
Subhadha? Alter title. It is change it. Same this. I to general for it.
Okay, so good evening and welcome you all to the guest lecture session of day 3. And it's a pleasure having Professor Satyonarayan Mukhopadhyay from Indian Association for the Cultivation of Science, Kolkata. And he is going to talk on a tutorial on the effective Lagrangian for Goldstone bosons. And all right, so with that, let us start.
Okay, so thank you. No? Battery? Is it okay now? Still not? It's okay? Hello? I think it's still.
It's better?
Okay, so thank you, Subhadha, for the invitation to this school. It has been a lot of fun already for the last 2 days, and expecting more in the coming 2 days. So, is it okay? I think it won't be better than this. You can hear me, right? Okay. So, I had started working on effective field theories right after the Higgs discovery in 2012, and we wanted to see if the operator structures deviated from the standard model predictions, how they affect the Higgs events, in particular the kinematics. And subsequently, I also worked on effective theories for dark matter later on. While recently I have not really actively worked on effective theories, but when Subhadha asked me to give a lecture, I thought let me go back to old times, and the oldest I could go back was the 1960s. When really the idea of effective theories were coming into play. In fact, there is a very nice story recalled by Steven Weinberg, who was one of the pioneers in this field. So, at that time there was no QCD in 1960s, and at that time they were trying to understand the dynamics of hadrons and mesons at low energies. and the main tools, because strong interactions are strong, so they could not do perturbative quantum field theory, and many people were losing hopes about quantum field theory. So, what they were doing instead was something called current algebra. So, which was basically studying the symmetry properties of different currents, and from current algebra they were trying to deduce rules for scatterings of pions, nucleons, and so on. And Weinberg writes that he had worked out using current algebra the amplitudes for a single pion emission and 2 pion emissions and so on in scatterings, and the more and more pions you include in current algebra, the computations get messier and messier. And he recalls that one day he was sitting in a cafe and writing down the formulae he got for multiple pion emissions, and on a napkin, and by staring at the results for the scattering amplitudes that he obtained, it occurred to him that he can in fact write down a Lagrangian and a quantum field theory from which all those scattering amplitudes followed, and the Lagrangian looked rather funny. So, the interaction, if I write down for the pions only that he thought will give the correct results, was of this form. So, this is in 1960s, and the interaction was of this form. Okay, so this was the Lagrangian, interaction Lagrangian. This is not something we usually write down when we do our basic quantum field theory course with the term v square minus pi dot pi in the denominator, right. But this rather funny looking Lagrangian reproduced all the results of current algebra, and this actually started the business of writing down low energy effective field theories which could describe pion nucleon scattering processes. At that time it was called phenomenological Lagrangians. Initially it was not called effective field theories. There is a very famous paper by Weinberg on phenomenological Lagrangians, and soon it was realized with the suggestion of Schwinger that in fact if one concentrated on the symmetries of the low energy interactions only and wrote down all possible terms allowed by the symmetries, then they should reproduce the results of the scatterings. And this is what we usually nowadays routinely say, right. The whole point of this effective field theory business is just you have your low energy fields and you know the symmetries, and you write down all possible operators that you can between those fields that obey those symmetries. That is what you have been doing for the last 2 days. And so, this was the beginning of such things, and there are reasons to believe that these pions were actually Goldstone bosons of certain broken symmetries. You might remember that pions are much lighter than all other hadrons. So, people wondered already then that why is pion so much lighter than the other hadrons, and Nambu actually proposed that pions may be the Goldstone bosons of a broken symmetry, and this understanding actually led to this Lagrangian that I wrote down here. And in today's tutorial we shall try to understand how this Lagrangian comes about. Okay. So, we will focus on the effective low energy Lagrangians for Goldstone bosons, and these are not just useful for describing low energy pion dynamics, they are useful for electroweak physics, which also you have been doing. As you know, in electroweak theory also you have Goldstone bosons, and it will be the same Lagrangian. So, the Lagrangian that describes pion physics will be exactly the same Lagrangian that describes Goldstone bosons in electroweak theory, standard model electroweak theory. And so, this is a very broad subject. In fact, the Goldstone boson effective Lagrangian actually shows all the features of effective field theory that you have been discussing so far. Now, I wanted to actually begin with this simple classification of these broad classes of effective field theories. One, excuse me, I might have to sit to write, but sometimes I will stand up, sometimes I will sit, because writing while standing is really difficult on this tab, and the board is very small. Broadly there are two types of effective field theories. One for which you already know the UV physics, and you can do a perturbative matching. Okay, you have been learning about that as well from lectures by Jose, Shubho, and Joydeep. And so I don't know where is the eraser, but anyway. And the other type is where you actually cannot do the matching. Now, you cannot do it either because you do not know the UV theory, or because you cannot compute things in the UV theory, right. So, the examples of the first type, where the UV physics is known and you can do perturbative matching, is for example the 4 Fermi theory, right, the classic example of effective field theories for which the UV theory is the standard model. Okay. And there are also things like heavy quark effective field theory, where you describe mesons with one heavy quark, or this non-relativistic effective field theories for QED and QCD. So, those are theories of bound states like the Onia. And the other type, which I said, where you cannot do the matching, either because you do not know the UV theory, or because it is too complicated to compute, maybe it is too strongly interacting. Now, the examples for where you do not know the UV theory is the standard model itself. So, there you do not try to match to any particular UV theory, you just write down all the possible operators that you can, right. You do not try to determine the coefficients by matching to some UV theory, or the Einstein theory of gravity, right. There also you do not know the UV theory, you can in principle actually go beyond the Einstein theory of gravity and write down all possible terms which are general coordinate invariant, right. So, that will be an effective theory at low energies, where you do not really know the coefficients, you cannot match to a UV theory. And the other class is where, as I said, that the matching coefficients are not calculable perturbatively, right, and the example for that is QCD, right. So, if you start with QCD and from QCD you want to obtain the low energy dynamics of pions and mesons, that is not possible, because QCD is strongly interacting and you cannot really match these two theories unless you do non-perturbative physics, right, unless you go to lattice, right. So, it is the second, this last class that is the business in pion physics, right, where I know the UV theory, which is QCD, but I cannot do a matching. So, I have to entirely rely on the symmetries of the low energy theory. And in order to discuss how this Goldstone boson effective Lagrangians look like before I go to pions, let me start with a very simple model where these features are all very clear. So, as I mentioned, for Goldstone boson physics, the main thing is the symmetry breaking pattern, right. So, there is some large global symmetry G, which is broken to some other global symmetry H, spontaneously broken, which gives rise to Goldstone bosons, right. You have all studied about Goldstone's theorem, and the whole point of Goldstone-Boson effective theory is that this symmetry breaking pattern determines the low energy Lagrangian completely. So, you just need to specify what is G and what is H. You do not even need to specify how the symmetry is exactly broken. Okay. For QCD, for example, we do have guesses, but no one knows for sure how the symmetries are, global symmetries of QCD are broken. And just this symmetry breaking pattern decides the physics, low energy physics of Goldstone bosons. And because the symmetry, this global symmetry group G and H are the same for this standard model electric theory and for QCD with two flavors, that is why the low energy Lagrangian for pions will exactly be the same as those for the Goldstones in the electric theory. So, that is what we see. So, let me then start by discussing this very simple model of spontaneous breaking of global symmetries, which I am sure all of you have studied earlier, but it is good to go through it again. So, spontaneous symmetry breaking of global symmetries. Well, so, the model that we will study is the so called sigma model. So, consider 4 real scalar fields, which I will put in a multiplet. So, phi is sigma pi 1, pi 2, pi 3. These are all real scalar fields, and they are described, the dynamics is described by a Lagrangian, which is the kinetic term minus the potential, which takes this very simple form, okay. So, this is the Lagrangian, 4 real scalar fields organized in a multiplet satisfying the dynamics is governed by this Lagrangian. Okay. Now, if this, so first of all, can you tell me what is the global symmetry of this Lagrangian? SO4. So, as you can clearly see that if you make a rotation among the elements of this multiplet, phi I goes to R I j phi j, where R transpose R is identity, then this Lagrangian remains invariant, right. So, it is a rotation of these 4 components, right, and this rotation group is SO4. So, R belongs to SO4. Now, there are 2 situations that are possible. One is that V square is negative, right. If V square is negative, the minimum is at phi equal to 0, all the components are 0, right. So, this describes 4 fields of the same mass, and that is it, the minimum is at 0, and the minimum still has a symmetry of SO4, right. If you are sitting at 0, you do a rotation, you still will sit at 0, right. So, the vacuum has SO4 symmetry if V square is negative, right. The interesting things happen if V square is positive, right. So, for V square positive, the minimum of the potential is for phi transpose phi equal to V square, correct. So, this is infinitely degenerate set of minima, right. There are infinitely many solutions that are possible, and they are given by this equation. So, let me put this symbol for the vacuum expectation value, and that is V square. So, these are the set of minima. Now, to do our quantum field theory, we need to choose a vacuum, right. So, choice of vacuum around which we will study fluctuations. So, choice of vacuum, this is arbitrary of course, but let me make a choice where somehow this is okay. So, let me make a choice which is expectation of phi equal to V 0 0 0. Okay. So, which means I have put the vacuum expectation value in one particular direction, right. Because of SO4 symmetry, whichever direction it is, I can orient it to one particular direction. So, this is without the loss of any generality. Okay. Now, does this vacuum have SO4 symmetry? No, because if your SO4 rotation touches this first element, then the vacuum will not remain invariant, right. So, this vacuum does not have SO4 symmetry. What is the symmetry of this vacuum? SO3. So, if I make a rotation of this among these last 3 components, right, the vacuum will still remain a vacuum. So, the symmetry of the vacuum is SO3, not SO4. Okay. So, symmetry of vacuum, and I shall denote the symmetry of the vacuum by H. Right, this is the symmetry of the vacuum. Okay. So, the symmetry breaking pattern then is from SO4 to SO3. Now, how many generators are there for SO4? Huh? Not sure? SO4, how many generators? 6? No, not for you. No, I really want them to participate a little bit, right. So, it has 6 generators, right, it is n into n minus 1 by 2, right. So, there are 6 generators, and SO3 3. So, the number of broken generators is 3. And by Goldstone's theorem, how many Goldstones should be there then in this theory? 3, right. Number of Goldstones equal to number of broken generators, right. So, this is the number of Goldstones. Okay. So far so good. So, we have 3 Goldstones. Now, let us define a shifted field as you usually do, because we do our field theories around fields with 0 vacuum expectation value. So, this sigma hat field will have 0 vacuum expectation value, it is just a shifted field, right. So, define sigma hat as sigma minus V and rewrite the Lagrangian, right. So, in terms of sigma hat, the Lagrangian will be the kinetic terms right, and a mass term for the sigma field, which is given by twice lambda v square, which you can easily check, plus some interaction terms m square over 2 v sigma hat into sigma hat square plus pi square and minus m square by 8 v square sigma hat square plus pi square whole square, right. This you can easily check. So, take the old Lagrangian, substitute sigma hat equals to sigma minus v, and you obtain this Lagrangian, right. So, what we see is that the sigma field has a mass 2 lambda v square and the pi fields do not have masses, as we expected, right. They are Goldstone bosons, they are massless. Right. Now, with this Lagrangian you can derive the Feynman rules of interactions between the sigma and the pi fields and compute scatterings between these Goldstone bosons, pi pi to pi pi scattering. Right. So, I want you to do this exercise. So, there will be some exercises because it is a tutorial. So, the first exercise is compute pi pi to pi pi scattering, 2 pi and to 2 pi and scattering in L sigma. So, in this theory. Okay. And after you compute it, expand in powers of energy over mass. Expand in powers of energy is energy of these pions and mass is the mass of the sigma, energy over mass, and determine the leading behavior in powers of E. Once you expand, you will know all the behaviors. This is a very important computation to do. Okay. This is a very simple Lagrangian, you have cubic and quartic interactions, just compute the pi pi to pi pi scattering. But remember to include all the channels. Okay. So, when you do sigma exchange, you will have STU channel, all of them are important. Okay. Just compute this and expand it in a power series in E over M. Okay. So, now we change gears. This is simple, this was just a review, and I change gears by doing something called a field redefinition. Now, it is not as simple as it sounds. There is a theorem in quantum field theory. Many people worked on this topic in again the 1960s. It is famously known as HIGGS theorem, but there are others also who worked on it. And in the context of Lagrangian field theories, it was Sidney Coleman who showed that if you have a theory which is defined by a Lagrangian, let us say theory of scalars to begin with, it is defined by a Lagrangian which is a function of the scalar fields and the derivatives of the scalar fields, and then you make a field transformation. So, you define new fields phi prime which are functions, I am writing the inverse transformation, but that is equivalent, which are functions of the old fields. Okay. You can invert this to obtain phi prime in terms of phi, right. So, you make a field redefinition and then you compute the transform Lagrangian. So, L prime phi prime del phi prime, which will be L of f of phi prime del of f of phi prime, right. So, you compute now the Lagrangian in terms of the phi prime fields. In general, you will get a new theory, right. You will get a new Lagrangian, right, depending on what the field transformation looks like, right. And the Green's function will also be different. So, now if you compute Green's function, different Green's functions, they will all be different, but under certain conditions the S matrix elements that you obtain by using these two theories will be the same. And the conditions are a little bit technical. They say that the Jacobian determinant at the origin should be 1. The Jacobian determinant of this transformation at the origin should be 1. As long as that is true, right, then these two theories will give the same S matrix element. Remember, the Lagrangian is different, the Green's functions are different, but the S matrix elements will be the same as long as that condition is satisfied. Okay. So, same S matrix elements under certain conditions, and what is even more important for us is that this statement holds order by order in perturbation theory. So, it is not S matrix elements to all orders that you have to compute to get the same answer in the two theories, but order by order the S matrix elements will agree. Okay. This is a non-trivial result, and I urge you to check that by doing a simple exercise. Take a free scalar field theory to begin with, right. So, take a free scalar field theory, del phi square minus del phi square by 2 minus m square phi square by 2. This is a free scalar field theory, and make a nonlinear transformation. So, define new fields such that phi is some constant plus chi whole square. This is a field redefinition. Okay. You plug that in. Now, you will have interactions between chi. The old theory was free theory, no interactions, but in the new theory you have terms like chi cube and chi to the 4th, those are interactions between chi. So, now compute chi to chi scattering in this theory. What should you get? Suppose this transformation is a good transformation, the Jacobian determinant is 1 at the origin. What? No, where is derivative coupling coming from? A is a constant. Yeah. What do you expect to get based on just the theorem that we discussed? Right. 0. You should expect to get 0 because it is just field redefinition from a free theory, but it is rather important to do this computation and see that you actually get a 0. So, it is a non-trivial computation. Okay. So, please do it. Okay. We need this result again and again, right. What I want to emphasize is field redefinition is not as simple as it sounds. Okay. If you want to look at the proof of this theorem, there are papers by Coleman, Sidney Coleman, for Lagrangian field theories that you may look up. Essentially, you have to go and look into the path integral first and so on, but anyway. So, with that out of the way, I will start now doing field redefinitions, right, because this theorem makes field redefinitions legitimate as long as they are proper. So, let me start by doing a simple field redefinition. Define a complex field which is a matrix, capital sigma of x is small sigma of x times the 2 cross 2 identity matrix plus I tau dot pi of x. These taus are the Pauli matrices. Okay. This is a field redefinition. Sigma is now a complex field, and it is. So, I am now making a field redefinition.
But what is the reason that you wanted to write it in this way?
Yeah, this it will become clear. Okay, at the moment it is just a field redefinition because it is legitimate to do field redefinition as long as the Jacobian is 1 at the origin. So, this is a complex field now, and it is matrix valued, and I claim that the Lagrangian for this should be, so you have to do the transformation of course, but I claim that the Lagrangian is 1 over 4 trace of del mu sigma dagger del mu sigma minus lambda over 16 trace of sigma dagger sigma minus 2 v square whole square. Okay, this is the claim. So, the claim is that this Lagrangian is same as the old Lagrangian with this field redefinition in view, right. You can very easily check this as long as you remember what is the trace of 2 Pauli matrices. Do you remember what is trace of tau A tau B? These are Pauli matrices. Anybody from the younger? Huh? It is actually twice delta A V, not delta A V. It is a trace, right. When you multiply, you get an identity matrix, but then you take a trace, right. So, it is twice delta A V. So, as long as you remember this trace, you can easily verify that this Lagrangian is same as the original Lagrangian that we started with. So, under the field redefinition, this is the Lagrangian. Okay. It is very easy to do, just take this trace. Okay. Now, let us figure out the symmetries of this Lagrangian. Okay. What are the symmetries of this Lagrangian? I claim that the global symmetry of this Lagrangian is SU2L cross SU2R, where these L and R's are just some labels, they do not mean anything at this stage. Okay. There are two independent SU2s and the global symmetry is a product of these two, okay. That is the claim. And under this symmetry, the sigma field transforms as follows. It is GR sigma GL dagger, where this GR and GL are the SU2 matrices. So, GR belongs to this SU2R, these are independent SU2s, and GL belongs to this SU2L. Okay. It is very easy to check that this is a symmetry, right, because once you put this inside this trace, right, what will happen? So, if you have trace of sigma dagger sigma, this will go to trace of GL sigma dagger GR dagger GR sigma GL dagger, and this GR dagger GR is of course 1, and now I need a property of trace to know that this is a symmetry, the cyclicity of the trace, right. So, trace are cyclic. So, if I can take this GL here by the cyclicity of trace, and then this is invariant, right, and as long as sigma dagger sigma is invariant, del mu sigma dagger del mu sigma is also invariant, because these are global symmetries, they do not depend on space times. So, they do not care about the derivatives, right. So, the symmetry of this Lagrangian is SU2L cross SU2R, that is the global symmetry. Okay. Now, you might wonder, I mean we had started with the Lagrangian with an SO4 symmetry, but now you have made some complex combination of those 4 fields and you claim that the global symmetry is SU2L cross SU2R, right. Now, there is a mathematical result that helps us understand this point, that if you consider the Lie algebra of these two groups. So, consider the Lie algebra of SO4, which I write as small SO4. This is same as the Lie algebra of SU2 cross SU2. Okay. This you can check, and therefore, these two symmetries are essentially the same as far as the Lie algebra is concerned, as far as the algebra of the generators of the symmetries are concerned. And you can also quickly check that the number of independent transformations is also same, right. SU2 has 2 square minus 1, 3 generators. So, 2 SU2s, so 3 plus 3 6 generators, and SO4 also had 6 generators, right. So, it is essentially the same symmetry, but because I have written in terms of a complex field, it appears in a bit different way. Okay. Now, having obtained this Lagrangian, let me make yet another field redefinition. So, today's tutorial is all about field redefinitions, many field redefinitions. So, one more field redefinition. Second one, where I go to polar coordinates. You will understand why I am putting so much effort in these field redefinitions. Okay. So, you can write down any 2 by 2 matrix as a magnitude, so modulus times a phase, which is a unitary matrix. Right. So, this is the decomposition of a 2 by 2 matrix, where this U is e to the power I over V tau dot phi. I have put the V to make the exponent of the exponential dimensionless. So, phi is a scalar field, it has dimension 1. So, I have divided by a mass dimension. The only mass dimension in the problem that we have is V. So, I have just divided by V. It is arbitrary, but okay. So, this is the new field. This is like polar coordinates, right. Now, u dagger u is 1. Can you tell me why? U is a matrix. So, again to the younger audience, why is u dagger u 1? Okay. So, it is an exponential of Hermitian matrices. So that will give you the proof that u dagger is 1. Good. Now, this is the transformation. Okay. The mapping is a bit non-trivial. This does not give the mapping explicitly, and given the time, I think I will give it as another exercise to compute the mapping. The mapping should be this: sigma of x is v plus s of x times cosine, this is a highly nonlinear mapping, mod phi by v, and pi of x is sine mod phi by v into phi x by mod phi. So, it is a really highly nonlinear mapping. Okay. So, your job is to prove that this is the mapping which gives this result. Okay. So, you just need to invert this equation. Okay. Now, given that we know how sigma, this big sigma transforms under SU2 left cross SU2 right, the question is how does u transform? Okay. U is the exponential of this pi's, right. Now, in order to see that, it is just sufficient to note that, so sigma, it just goes to gr sigma gl dagger under G. So, you just note that in sigma I have a modulus v plus s of x, but this does not have any matrix indices. So, this will just come out of the sigma, and all the matrix indices are contained in u, right. So, it must be that u also transforms in the same way. You understand, right, because these gr and gls are matrices, right, they will act on some matrix indices, right. V plus Sx has no matrix index, right. So, this field S is then a singlet under these transformations, and u transforms in this way. Yeah. Yeah, it must be, right, because it multiplies the whole thing. Yeah, thanks. So, if you did the exercise, you will find out the errors. So, please do them. Yeah, I do not guarantee that there are no errors, there may be errors. So, please yeah, I just did some computations, right, I mean I do not know. Okay. Okay, so all of you are fine with this, that under this global symmetry G, this exponential matrix U transforms as GRU GL dagger, fine. Okay. Now, what is the symmetry of the vacuum? So, the vacuum, all the vacuum expectation value has been put in the modulus part, right. So, in the vacuum, all these phi fields take vacuum expectation value 0, right. So, in the vacuum, this U is an identity matrix, correct. So, the vacuum expectation value for sigma is simply V times the identity matrix, correct, because U is identity in vacuum, all the phi fields are 0 in the vacuum. Now, is this SU2 left cross SU2 right a symmetry of this vacuum? What do you think? you can just check, right, how does it transform, right. So, this will go to GR vacuum G left dagger, identity will just go through. So, it is V GR GL dagger. Is this one? It is not. So, it is not V. So, this full group G is not a symmetry of the vacuum. What is the symmetry of this vacuum then? Which one? L equal to R, right. So, if GL was GR, then this is the symmetry of the vacuum, right. So, symmetry of the vacuum is GL equal to GR, right. So, it is one SU2 and this is known as the vectorial SU2. So, let us call it SU2V. Okay. So, the symmetry breaking pattern, so this is our H, right, is then SU2 left cross SU2 right going to SU2V, and there are 3 goldstones as before, right, 6 in G, 6 generators in G, 3 in H. So, there are 3 goldstones. The number of goldstones of course will not change, right, the physics will remain the same, it is just field redefinitions, right. So, now with this compute, let us compute how the Lagrangian looks like, right. So, remember our old Lagrangian, right, it was I can go up, so that is good, this one, right, 1/4 trace of del mu sigma dagger del mu sigma minus lambda over 16 trace of sigma dagger sigma minus 2 V square, right. So, you plug in this sigma V plus S of x times U of x in this, right, because V plus S of x has no matrix indices, all the traces will act on U, correct, U has the matrix indices. So, if you just plug this in, you will obtain 4 terms in the part where we have trace of del mu sigma dagger del mu sigma. There are 4 terms to begin with. The first 2 are very easy. You will obtain del mu s trace of u dagger u plus V plus S whole square. You can almost read this off, right, just by looking at that Lagrangian del mu u dagger del mu u, right. The trace acts only on the u's. So, these are the square terms. Now, there are 2 cross terms, right. The 2 cross terms are as follows: del mu s trace of u dagger del mu u V plus S plus del mu s trace of del mu u dagger u. So, this is the del mu V plus S. Okay. Now, can you try to simplify these cross terms? So, of course, del mu s is common, V plus S is common. So, it is a sum of trace of u dagger del mu u and trace of del mu u dagger u. Can you see a simplification? It is kind of staring at you. No? Derivative of? Very good. So, it is derivative of u dagger u, right. So, if you add these two, you get trace of del mu of u dagger u, and you can take the del mu outside the trace, right. So, it is del mu of trace of u dagger u, but u dagger u is identity, right. So, this del mu of that is 0. So, these last 2 terms add up to 0, clear, right. U dagger u is identity, remember that, it is a unitary matrix, you understand, right. So, the last 2 terms will add up to 0 and we are left with these first 2 terms. The potential is very easy to calculate, just take trace of sigma dagger sigma, you will just get 2 into V plus S whole square, because U dagger U is 1. So, what is our Lagrangian then? So, our Lagrangian after plugging all this in is as follows. So, let us start with this U part, which contains the goldstones, right. So, this term, remember there was a coefficient up front, right. So, this yeah, there is a 1 over 4 trace of del mu sigma dagger del mu, right. So, 1 over 4 was there. Okay. So, then we have, let me take a V square common. So, V square over 4 1 plus S over V whole square trace of del mu U dagger del mu U plus the Lagrangian, which involves only the S field. You can easily check the mass term for the S and the whole Lagrangian for the S is actually the same as the one for sigma. In fact, if you have followed your lectures so far on the standard model given by Subhaditya, you should be able to recognize this Lagrangian for S. Does it look familiar? The Lagrangian for S? Just S. Sorry? Yeah, it is a Higgs Lagrangian. It is exactly the same Lagrangian as for the Higgs. Okay. Now, let us focus on the Lagrangian for the Goldstone bosons, which we thought of discussing today. Suppose I work in energies much less than the mass of this S field M. Then I can integrate out the S field. Okay. So, then at the leading order, the Lagrangian for the Goldstones becomes V square over 4 trace del mu U dagger del mu U, right. Integrating out at leading order means you can simply erase this. Okay. At higher orders, of course, you have to compute S exchange diagrams and see which operators they give, right. So, this is the leading order term in the Lagrangian for the Goldstone bosons, and you see that they involve this term involves 2 derivatives. So, whatever couplings that we are going to get for Goldstone bosons will involve at least 2 derivatives, right. Now, having derivatives in interaction means in the Feynman rules you will have momentum factors, right, or energy factors, right. So, the leading contribution will be of order E square, right, because of the 2 derivatives in the amplitude level, right. In particular, as E goes to 0, the amplitude for Goldstone scatterings will go to 0, right. In fact, this dependence on the energy gives us a handle on this expansion in terms of effective operators for Goldstone boson scatterings, because at low energy the couplings become weak, they are proportional to the energies, right. So, we have an expansion, right. The expansion will be as a series in E over V, right. As you will soon see, all the interaction terms will come with factors of 1 over V square. Okay. So, it will be an expansion in powers of E over V, and at low energies this is a controlled expansion, right. Otherwise, there are infinitely many terms actually in this trace of del mu U dagger del mu U. So, already at leading order there are infinitely many interaction terms. Right. Let us see what those are to begin with. So, if you expand this this term with u equal to e to the power I over v tau dot phi. So, you just expand, you will obtain the following kind of terms. So, this is the Goldstone Lagrangian, half del mu phi dot del mu phi. So, the factors that we have put in like v square over 4 which came in our calculation are all correct, because our kinetic term has the canonical normalization which we must recover. Okay. The first interaction term will be a 4 Goldstone interaction involving 2 derivatives. And then there will be a term of this form and so on. So, what I am doing is I am simply expanding this u as a Taylor series, right, taking the derivative, multiplying them up and getting these terms. So, I kept only up to the squared term in the expansion and got these terms, right. If you keep higher and higher terms, you will get interactions. So, this is already 4 Goldstone interaction. So, 4 Goldstone, let me write gold for short, but yeah, and 6 Goldstone, 8 Goldstone and so on. Now, you see that they come in even numbers, right, 4, 6, 8 and so on. So, it is another exercise to figure out why they come in even numbers, but can you guess? What can be the reason that the odd terms must vanish? Huh? Yeah, what kind of symmetry will lead to the odd terms vanishing? Huh? You said Z2? No, it is a parity actually. So, you will see that this Lagrangian has a parity symmetry and these Goldstones are actually parity odd. Yeah. So, because of parity, but first do the computation and see that the cubic and the, all those odd terms are 0, then go back to the Lagrangian and see that parity is symmetry. The important point to note is that phi right, but phi dot phi, all the phi's transform in the same way under parity. The remnant symmetry is there of course, but parity is also a symmetry and that actually prohibits the odd terms. I do not think the vector symmetry will prohibit the odd terms. Yeah. So, please check. The important point to note is that all these 4 Goldstone, 6 Goldstone, 8 Goldstone, all these interactions at this order are given by a single parameter v square, right. So, all these interactions at this order are fixed by v square. So, if I can somehow measure v square, right, by measuring the amplitude for a single process, then I will know the amplitude for all the other processes, right. Okay. Now, so far the discussion was quite generic. What does this have to do with QCD? Right, this was just a model. Right. There was no QCD here, right, but I still claim that this is not electroweak. You can still understand, right, everything looks like the Higgs symmetries. So, that is okay. These are this is the Lagrangian for electroweak Goldstones as well, right, but what does it have to do with QCD? Now, originally the fact that this is also low energy Lagrangian for meson scattering came from understanding the phenomena of mesons and realizing that the low energy phenomena of mesons and mesons obey this kind of a symmetry breaking pattern. Okay. So, low energy meson phenomena, right, because they did not know about QCD at that time. Right. So, the study of these currents that I mentioned. However, since we know about QCD, let us just look at the quark part of the Lagrangian for QCD. So, L quark in QCD, right, is q bar I d slash q. Oh, QCD with mass of quarks as 0, QCD with MQ0, and just consider two flavors. So, consider q equal to ud, two flavors. So, these q's are column in this flavor space, right, just u and d. They also have color indices, but I am suppressing those color indices. Okay. Now, this is same as ql bar I d slash ql plus qr bar I d slash qr, right. You can easily check this. You know what this L and R mean, right? It is 1 minus gamma 5 by 2 is PL and so on. Okay. Now, you can immediately see that this Lagrangian has this SU2L cross SU2R symmetry, under which this QL transforms as GL QL and the QR transforms as GR QR, two independent SU2s, right. These matrices GL and GR are in the flavor space, 2 by 2 matrices. They do not act on the Dirac indices or the color indices, they just act on the flavor indices, this U and D, right. And it turns out that the spectrum of low energy, spectrum of mesons that we see, they do not have this SU2L cross SU2R symmetry. Okay. So, the symmetry of the Lagrangian is not respected by the spectrum. Now, the spectrum reflects the symmetry of the vacuum, because the mesons that we see are excitations over the vacuum, right, and the mesons show a single SU2 symmetry, so called SU2V. So, therefore, the spectrum implies that this SU2 left cross SU2 right symmetry that exists in the Lagrangian is actually broken to SU2V. Now, given the fact that the symmetry breaking pattern is the same as we studied before, even though this is not the same model, it is a theory with quarks, right, which eventually become mesons after confinement, still because the symmetry breaking pattern is the same, all the Goldstone dynamics is the same, as we emphasized. So, the Lagrangian that we wrote down, this Lagrangian must be the leading order Lagrangian for pions. So, if you want to compute pion-pion scattering, you can compute it at leading order just by using this Lagrangian. Okay. And the symmetry breaking happens in a very different way in QCD. It is believed to happen through a condensate of q bar q, which breaks this SU2L cross SU2R, right. The mass term breaks SU2L cross SU2R, q bar q respects SU2V. Okay. So, the mechanism of symmetry breaking is very different, but as I emphasized earlier, it is just the symmetry breaking pattern that determines the low energy Goldstone boson scattering Lagrangian, right. It does not matter how the symmetry was broken, as long as the G and the H are the same, everything is same. So, the low energy scattering of pions is described by exactly the same physics as for the electroweak Goldstones. Yeah, just let me complete and then I will come back, because we are running. Yeah. Okay. Now, before I end, I would like to give you two more exercises. The first one is that now we have a Lagrangian which shows that Goldstone boson scattering at leading order should go as E square. So, if you compute with this Lagrangian now pi pi to pi pi scattering, that should have a leading behavior of E square, right, and because the Lagrangian has two derivatives, right. But remember this Lagrangian we started with, there was no derivative at all for the Goldstone interactions, It was all cubic and quartic interactions. And I gave you the exercise that compute the pi to pi scattering with that Lagrangian, do an expansion in E over m, and find out the leading term in the energy expansion. So, you already know the answer you should get. It should be proportional to E square. This Lagrangian makes it very clear. It makes it very clear because we chose our coordinates very carefully. We chose the angular directions as our Goldstone coordinates, right. And the moment you choose the angular directions as your Goldstone coordinates, the symmetry of the theory of the vacuum is reflected as a shift symmetry, right. The angles shift under these rotations, and because the Lagrangian should be shift symmetric, it can only contain derivatives. Right. In the previous Lagrangian, this fact was hidden. Right. So, as long as you do that computation correctly, the leading behavior should be E square. And now you know how to write down the higher terms that Jose had written, right. The next terms will contain even more number of derivatives. So, try to write down terms with 4 derivatives, right. You can think of all the possible terms that you can write down. Okay. Lastly, I would like to end with what I started with. I said that low energy pion scattering, Weinberg said, obeys an interaction Lagrangian of the form pi dot del mu pi whole square by v square minus pi dot pi. But this looks very, very different from what we wrote here, is trace of del mu u del mu u. So, there must be another field redefinition that gives you this Lagrangian. So, I want you to determine the field redefinition that will lead to this Lagrangian starting from the initial sigma model that we have written. And in this respect is the following. If you think about it carefully, if you have a SON symmetry which the old sigma model had broken to a SON minus 1 symmetry, then the Goldstone bosons live on the surface of a sphere Sn minus 1. Okay. This you can show. Just study the equation describing the Goldstone bosons, and they live on the surface of a sphere. So, they are constrained to live on the surface of a sphere. Now, the surface of a sphere is described by an equation of the form pi 1 square plus pi 2 square up to pi n square equal to v square. The radius of the sphere is this v. Okay. The radial excitations are actually change in the radius of the sphere, and the Goldstone excitations are all movements on the sphere. Okay. So, you have a constraint equation pi 1 square plus pi 2 square up to pi n square is equal to v square. Right. But with constraints fields, you cannot do your quantum field theory. You have to choose a set of independent fields. So, eliminate one of the fields by using this equation. Right. You can immediately see, so suppose you eliminate pi n, right. So, pi n square can be written as v square minus pi 1 square and so on, and given that this Lagrangian immediately follows. So, just complete the steps and we will come back full circle. Okay. So, I would like to end with that. Thank you. Yeah, now we can come back.
Questions? Yeah. Sanjoy.
No, you just said that the quark mass term break the symmetry, you said, right?
Quark mass terms do not respect the SU2L cross SU2R symmetry.
Yeah, but anyway, that was already broken by the vacuum expectation value of the QQ bar bound state, right? Spontaneously.
Well, I mean,
that was the explicit breaking.
Yeah. So, this step came before. So, why I was not writing the quark mass terms to begin with, right? Because they break the SU2L cross SU2R symmetry explicitly, and now we do not know what the QCD dynamics does, right. So, it must be, whichever way the symmetry is broken, it must be through the vacuum expectation value of an operator, right. Now, this operator QR bar QL actually breaks the axial vector symmetry, and we know that the axial vector part is broken. So, this is the simplest operator that will break the axial vector symmetry and keep the vector symmetry intact, which is realized in the meson spectrum. There can be other operators, right, but people have calculated these operators on the lattice, right, and it seems that you can have chiral symmetry breaking through expectation value of the operator, but unless we do non-perturbative physics, we have no idea to know. But this is the simplest operator that will break the axial vector symmetry. we already had some discussions, but if you have more questions.
More questions?
So I hope I made this point home that the Goldstone boson Lagrangian represents everything that you have learned about effective field theories. You have a low energy symmetry, you know the low energy degrees of freedom, right. The low energy symmetry is whatever this H, the low energy degrees of freedom, the Goldstones, and just the symmetry breaking pattern determines the Lagrangian for the Goldstones. This is IR physics, right. This says nothing about the UV physics. The parameter that is sitting there, the V, that is determined by the UV physics. That is different in the standard model and in QCD, right. In standard model is 246 GeV, in QCD is 130 MeV. Okay. That is determined by the UV physics, but the effective field theory does not know about the UV physics. Okay. It is only the IR physics that knows, and it is a controlled expansion. In this case, the controlled expansion is in powers of E square over V square. Right. So, you can write down many more terms, you can calculate loops also, right. Still it will remain a controlled expansion. Of course, the loop diagrams will be divergent, you cannot absorb all of them at a certain order, you need to include higher order terms, but once you do that, again it will become renormalized, right. So, it is a very controlled theory where you can make predictions, compare with experiments, and it is a quintessential effective field theory. B.
So is it related to QCD scale?
It is the pion decay constant.
Okay.
Yeah. Right. So usually it is determined from the decay width of the charge pion because it couples to this axial current. Yeah.
So I thought about that alpha running of QCD that starts diverge around lambda equal to 20.
Similar scale, but here is the pion decay constant. Yeah, there is a question.
Is it correct to say that this SU to L cross SU to R is equivalent to SU to axial vector cross SU to vector, and then the when the quark gets the the condensation happens, this axial part SU to axial is basically broken down.
Correct. So the vector generators are L plus R generators, axial are L minus R generators. So it is correct.
Okay.
You can work with both of them. The commutation rules will be different, right, depending on what you choose. Right. So in the SU to R, L cross SU to R thing I wrote down, the commutations are especially simple, right. But in the one you said, they get mixed up, and then it will be different. Yeah. But the physics is the same. You're right.
Can you write a flavor changing operator and match with this chiral perturbative Lagrangian?
No. So I am trying to describe mesons.
Yeah.
And the theory that I did was SU2 cross SU2. So it just described pions, right. So all the interactions of charged and neutral pions are described by this Lagrangian.
So like in QCD, so there is a U and D quark U.
Yeah, but this Lagrangian is not about U and D quarks. It is about the low energy degrees of freedom.
Low energy degrees of freedom.
Pions.
So if you take some corresponding Wilson coefficient and their flavor changing operator that it mixes with U and D. I mean not U and D, like yeah.
Okay. No, so as I said, pi plus pi 0 can have scattering amplitudes which are non-zero. It describes all of this, right. What you are trying to suggest is that there is a flavor mixing in the QCD Lagrangian. That is not the case. The QCD Lagrangian has no flavor mixing.
So not at the tree level, but as the effective operator, like some loop suppression operator. Yeah.
You may write down, but I don't know what that will do because we cannot match. See, I began with the fact that there are theories in which you cannot match, and there are theories in which you can match. We are discussing a theory in which we cannot match, and it's only this global symmetry breaking pattern that we can see in the low energy meson.
Only diagonal quarks are there in that case.
Yeah, the QCD Lagrangian has only diagonal quarks.
Yeah.
More questions?
So maybe after you do the exercises, you might have more questions. I am around. So please catch me.
Yeah.
And,
so 2 more days to go. So you have time to finish those exercises also. Okay. If no more questions, let's thank Shotto for a nice talk. And we would like to do the honor of felicitating him. Okay, so we don't go home now. We have another assignment, which is we would like to get introduced to all of you who have come to attend this course. So maybe what we can do that we can start from the last, is it? And you should tell your name, the place that you are coming from, the things that you are doing, and something. Yeah.
So, hi everyone. I'm Saurav, and I'm a first-year PhD student at IIIT Hyderabad. And currently, I'm working in cosmology, so inflation models and reheating models, and the other things. So, most of the time, I'm involved in my course completion and all, but yeah.
Hello everyone, I am Manas. I am a PG student from NIT Agartala. I have worked on neutrino physics at GUT scale. So yeah, that's all for me.
Hello everyone, my name is Maz. I am from IIIT Hyderabad. I work with Subhaditya Mitra. And I'm a third year PhD student. My work is mainly quantum information theoretic observables and their use at colliders, how to measure entanglement and all.
Hi everyone, my name is Sirin Neeraj. I'm also a PhD student at IIIT Hyderabad. I work on BSM phenomenology focused on vector-like quark models and application of machine learning at colliders.
Hello, my name is Darji Shamir. I'm a second year PhD student from IIIT Hyderabad. Presently, I'm now working on implications of post-Bell2 results in lambda B decay.
Hi everyone, I'm Sitesh. I am from IIT Guwahati and I work in cosmology and most particularly in the magnetohydrodynamic study in the early universe.
Hello everyone, I am Vipin Anand. I am first year PhD student at IIT Guwahati. I have joined under Dr. Subhaditya sir, and my topic of the PhD is in cosmology, dark matter physics.
Hello everyone, I am Tanmay Dev. I am second year PhD student from Guwahati University. I am working on QCD, mainly tetra quarks and pentaquarks.
Hello everyone, my name is Shivam and I am postdoc here and I work on dark matter, axion, ineffective and related BSM phenomenology.
Hi everyone, I am Prachiti. I am from ICER TVM. I work with Professor Matthew Arun Thomas and I am currently a master's second year student and I dabble in CPE violation. So I especially thank the organizing committee and Subhaditya sir because for accommodating me here. I really wanted to know what I don't know and there's a lot. Thank you.
Hello everyone, I'm Raisa Imtiaz. I'm from Dibrugarh University and I just started my PhD on neutrino physics. Yeah, thank you.
Hello everyone, I am Tisha from IIT Kanpur. I have recently joined Joydeep Das group and working on the top-down EFT approach. And I did my PhD in collider phenomenology with application in the EFT.
Hi, my name is Atanu Samanto and I am working I am doing PhD at IIT Kanpur and I am working on heavy QCD LP. Thank you. Thank you.
Hello everyone. I am Devallo from IIT Kanpur, and I'm working under Professor Joydeep Chakraborty. And currently, my research work is based on only on theoretical particle physics, and mostly on using a certain method, using the right now the heat kernel method, where in contrast with the generic the Feynman method, where we compute effective action and all those things. So yeah, that's it.
Hello everyone, I am Debanjan Balui. I am a third year MSc PhD dual degree student from IIT Kanpur. I am currently working under Professor Joydeep Chakraborty. I am currently studying the heat kernel formalism.
Hello everyone, I am Ankit Das. I completed my masters at IISER Kolkata, and currently I am at IIT Kanpur as a project student, and I am interested in theoretical particle physics. Yeah.
Hello everyone, myself Jainam Savla. I am from IIT Gandhinagar, PG second year, and I am working under Dr. Bharadwaj Kolepa sir, who is also high energy phenomenologist. My project title is currently Higgs effective field theories and studying its applications. So it's very nice to see all the talented people working here and asking questions and learning together.
Good evening everyone. I am Saurabh Purohit from Odisha. I am now working under a project, Mukhyamantri Research Innovation Program of Odisha. Now I am working as a project assistant in Odisha. Besides this project research work, I work for stage program like writing articles, slam poetry, this type of program. Thank you Subhaditya sir for arranging this.
Yeah, hi, I am Shoman. I am a final year PG student here. I work under Professor Obrangsushil, and I mainly work on dark matter phenomenology and little bit action and action-like particles phenomenology. Thank you.
Hello everyone, I am Anas De. I am a research scholar at the Department of Physics, Guwahati University. Presently I am working in neutrino physics phenomenology.
Hello everybody. I am Nipanka. I am a first year PhD student from Beach Pilani, and currently I am working on 2x doublet model to search for dark matter candidates.
Hi, I'm Cheshta and I'm working with Professor Rusha Mandal at IIT Gandhinagar. I'm currently extending my master's thesis, which explored the reasons for quark mass hierarchy, and currently I'm doing a junior research fellowship where I'm exploiting CP violating signatures in B meson decays. Thank you.
Hello, my name is Pradeep Singh Shekhawat and I'm a first year PhD student at IMSC, and currently I'm doing my coursework, but hopefully I'll be working on particle physics.
Hello, I am Anupam Ghosh. I recently joined Dr. Subhaditya's group and I did PhD from PRL, and I do works on the colloidal phenomenology, dark matter, axions and...
Hi everyone, I am Shashwat Sharma from IIT Hyderabad. I am under Professor Narendra Sahu, and I am currently working on various models of leptogenesis, and currently I will be going for gravitational leptogenesis.
Hello everyone, my name is Debolina Nundi, and I am a first year PhD student from IIT Guwahati itself. I am working under Dr. Debashish Bora, and hopefully the broader area of research of mine is going to be the baryogenesis, specifically the gravitational imprint of the baryogenesis. Thank you.
Hello everyone, my name is Sonakshi Shah. I am first year PhD student of IIT Guwahati, and I am working under Dr. Soumitra Nandi sir, and my research topic is, I think, cosmology, dark matter related things.
So myself Deepankar Pradhan, I am working under I am working under Subhaditya sir, and my area of basically dark matter, phenomenology, cosmology, and also neutrino phenomenology.
Hello everyone, I am Lipika and I am from IIT Guwahati, and I am working with Dr. Soumitra Nandi in flavor physics and cosmology.
Hi, I am Soumujit Dotto. I am integrated BSM student from IISER Kolkata.
and I am working under Professor Subhaditya Bhattacharya on my MS project on some particle phenomenology.
Hello everyone, I am Bikash Kumar Acharya. I am currently a second year PhD student at ISER Berhampur. I work with Dr. Ujjwal Kumar De. We at our group do gravitational waves, BSM phenomenology and neutrino physics. Thank you.
So I am Pramod Sharma from ISER Mohali. I'm PhD student, and I am working. I do basically PSM phenomenology, mostly model independent way. I also do higher order corrections as well.
Hello everyone, my name is Shampriti Roy. I am from ISS Kolkata. I am a second year PhD student under Dr. Shatyaran Mukhopadhyay. Currently I am trying to learn finite temperature field theory.
Hello everyone, my name is Kaustav Mukherjee. I am from ISS Kolkata, working a fourth year PhD student working under Professor Dilip Kumar Ghosh. I mainly work on cosmological phase transition and gravitational waves.
Hello everyone, my name is Krishna Tiwari. I am a second year PhD student from RKM Very Belur. Currently I am working on dark sector and portal matter phenomenology. Thank you.
Hello everyone, my name is Shivam Verma. I'm working with Dr. Sanjay Viswas at RKM Very Belur. Currently we are working on collider phenomenology of vector-like fermions and also applying machine learning techniques to tag some BSM particles.
Hello, I am from RKM Very Belur, Orko Bhattacharya. I am first year PhD student working on finite temperature, field theory, electric phase transition, etc.
Hello, I am Rajiv from PRL. Earlier I worked on B physics in EFT framework. Right now I am exploring neutrinoless double beta decay and lepton number violation in the EFT framework.
Hi, myself Avnish, and I am now postdoc here, and I'm very soon going to watch postdoc here. So collider physics, phenomenology and dark matter phenomenology have been my past and current interest. Now I'm finding, thanks to Jose, that I'm finding and other fellows, I'm finding effective field theory also very fascinating. So hopefully I will also pursue this. Thank you.
Hi, I am Shomudeep. I am from ISER Trivandrum. I am working with Dr. Tanumay Mandal, and our group is especially interested in BSM phenomenology, and currently I am working in the leptoquark models.
Hello everyone, myself Nitesh Kumar Meher. I am a MSc second year student here, and I am doing a MSc project under Subhaditya sir on Higgs physics.
Hello everyone, my name is Chandra Prakash, and like him I'm also doing second year master's program here, so I'm not working on anything specifically. However, as part of my master's program, I'm working on early universe, specifically trying to understand the observational signature of inflation, reheating, and the subsequent events that followed after that, and trying to understand how we could observe them in CMB and through gravitational waves. Thank you.
Hi everyone, myself Sai Gade. I came from Hyderabad, and I'm a prospective PhD student. I have done my masters at University of Hyderabad under Professor Rukmini Mohanta, and I have did a project beyond standard model where I incorporated dark matter and stuff. And right now I'm working on lepton number violation rate decays. And thank you.
Hello everyone, I am Abhishek. I am PhD student from IIT Delhi. I am working with Professor Abhishek Iyer, and currently we are working in composite Higgs model.
Hi everyone, myself Sultu Manna from ISER Berhampur, second PhD student. I am working under Ujjwal De, and I am currently working in electric fast order phase transition and gravitational wave signature.
Hello everyone, I am R. Tiruchendil, postdoctoral fellow at Institute of Physics, working in neutrino physics.
Hello everyone, I am Shubham from Institute of Physics,
I am working under Dr. Maniwala Mitra, and I am working in collider phenomenology in right-hand neutron effective field theory and some machine learning to distinguish between signal and background and like that stuffs.
Hello everyone, I am Shongshaptak, currently a postdoc at Institute of Physics, and I work mainly in collider phenomenology and search for BSM physics at future colliders. And I'm also interested to apply machine learning in my search for BSM physics.
Hello everyone, myself Akinchan Kundu. This year I just completed my masters from Presidency University, Calcutta. I worked on the Lorentz invariance violation with neutrinos sector. With my guide was Debanjan Bose sir in collaboration with Munmun Devi ma'am from Tezpur University. Currently, as I just mentioned that I just completed my masters, I am looking for the projects on various aspects in neutrino physics particularly to explore this area before doing PhD. So, thank you.
Hello everyone, I am Shreya Kormakar. So I also recently finished my masters from Tezpur University. So my master's thesis on neutrino physics, specifically on neutrino mass model. Thank you.
Good evening, my name is Aisha Zaika. I also completed a master's from Tezpur University. I am working on ring down analysis in gravitational waves, also studying the memory effects due to dark matter candidates, and also studying some compact objects. Thank you so much.
Good evening, everyone. My name is Dr. Maibam Riki Devi. I am the guest faculty from Department of Physics, Guwahati University. During my PhD, I have worked in neutrino physics. Currently, I am working specifically on modular symmetry, higher order modular symmetry based neutrino models, as well as I am working on gravitational waves.
Evening everyone, myself Rakesh Kumar. I'm currently working with Basabendu department and at SRM AP. My interest is to explore new physics with primordial gravitational wave in the landscape of early universe. Thank you.
Hello everyone, I am Shaumen Roy, a PhD student from IIT Guwahati. I am working with Shobhan Chakraborty, mainly working on neutrino physics, alternative cosmic ray and dark matter decays. Thank you.
Hello everyone, I am Pratyay Chandra. I am a first year PhD student at IIT Kharagpur and working under supervision of Professor Titto Shankar Ray. So I will be working on astroparticle physics. Thank you.
I am Suresh Chand. I am PhD student from IIT Guwahati. I am working on dark matter and leptogenesis.
Hi, I am Radhika. I am from IISER Mohali. I did my PhD in collider phenomenology and presently working on phenomenology of simplified dark matter models.
Hello, I am Subhaditya. I am doing my PhD from this university, IIT Guwahati, and I am interested in BSM phenomenology via effective field theory.
Hello everyone, myself Surendra. I am second year PhD student at IIT Guwahati, and I am working under MK Nandi and basically work on baryogenesis and leptogenesis.
Hello everyone, my name is Utsab De. So I'm a final year research scholar of this IIT Guwahati. I'm working under the supervision of Dr. Soumitra Nandi, and my research area mainly focuses on the phenomenological analysis of BC mesons and other B meson inclusive and exclusive modes. Thank you.
Hello, I'm Deependu Bhandari. I'm a PhD student in IIT Guwahati. I'm currently working on Professor Onang Sushil, and my research topic currently is electric baryogenesis mechanism, dark matter, and various aspects of phase transitions.
Hello everyone, myself Indrajit Shah. I am from this IIT Guwahati, and I am working on cosmological phase transition in BSM scenarios, working under Debashish Bora.
Yeah, I am Obik Sarkar. I am one of the teaching assistants of this course along with Niloy. So I work mainly on collider physics concerning dark matter, Higgs and efficiency.
Myself Niloy, I am working under Subhaditya sir, and I am currently working on leptogenesis, little bit dark matter and neutrino physics.
Okay, so that was a nice session to know that many of you have traveled long distances to come to this part, and hopefully we are not boring you to a great extent, and it has been a fruitful 3 days so far. So we next couple of days will be exciting as we go along, and we have 4 more lectures by Jose and 2 by me, and we have 2 more guest lectures, as you can imagine, one by Shankho, who will talk tomorrow, and Shoumitrada is going to finish on the last day. So okay, with that note we finish today, and we see you tomorrow. Have good rest and enjoy the evening.